Hello my beautiful PU2 aspirants, I know your exam is knocking your door. So in this particular moment, I am here with full physical chemistry. So here in this one video, all doubts in physical chemistry is going to be sorted. So all probable question, maybe it's MCQ, maybe it's theoretical 2-3 marker, or maybe it's a numerical based question. I am going to give the answer here itself and the derivation as well. So make sure you are watching the full video, and expected from these questions only you are going to get the question in your upcoming examination. So these questions are precisely have been chosen from the model papers, from the question bank, and by judging all the trends in the previous year questions. So make sure that you are not missing a single point out of it. So yes, to get to know the detailed answers of the most important question, watch till end. So a lot of things I have to tell, a lot of question we need to discuss. So yes, without further delay, let's get started with the first chapter, because only 3 chapters are there in your physical chemistry, that is solution, chemical kinetics and electrochemistry. Only these 3 chapters will be covered in this video. Okay, so let's start with the solution chapter. Here comes the entire formula chart for the solution chapter. You can take a screenshot or whatever you wish, you can make a note of it. Only in these formulas you are going to get the numerical or maybe theoretical questions. Okay, let's proceed. Okay, so it's a general question. What is molarity? How does it vary with temperature? How does it vary with temperature? What is molarity? That I don't have to tell. The number of moles of solute that is present in 1 liter of the solution, that is a molarity. How does it vary with temperature? So molarity, if you write, then number of moles of solute divided by volume, right? Volume of the solution. Now volume and temperature, if you see, volume and temperature, they are directly proportional, right? So for that perspective, molarity and temperature, they are inversely proportional, right? Because molarity and volume, they are inversely proportional. So molarity and temperature, they are also inversely proportional. Okay, so what is the SI unit? Okay, what is the SI unit? Mole per liter. Mole per liter. Okay, let's proceed further. 3 marker question we are entering. Application of Henry's law to prepare definitely carbonated beverages. There are application of Henry's law, and scuba divers, right? Scuba divers, they faces bends when they go deep down to the ocean, right? Because of the dissolution of nitrogen gas in the blood. But now to prevent this, they actually mix helium. In some certain amount of helium they are mixing to prevent the bend. That can be well explained using the Henry's law. Next is anoxia. Anoxia is something that the higher altitude people, they used to face because of the lesser amount of oxygen in low pressure. In the higher altitude they actually get, and brain doesn't get enough supply of oxygen, hence they get some dizziness, this type of thing. Okay, nausea, because of the lesser oxygen in the brain, right? So that can be well explained using the Henry's law. It's clear, I guess. Let's proceed further. It's from the solubility. State Henry's law, write its mathematical form. So I don't have to tell it differently. You can directly write this statement that the solubility of gas in a liquid is directly proportional to the partial pressure of the gas. Okay, mathematical form you can write P equals to KH into X. Make sure that you are writing the abbreviation correctly. Okay, next, what is the significance of Henry's constant? So KH, what is the significance of KH? KH actually gives the solubility of a gas at a given pressure. Okay, so higher the KH value, it indicates lower the solubility because they are inversely proportional, right? Let's proceed. Okay, the question is, derive its mathematical expression of vapor pressure for a solution of a non-volatile solute in a volatile solvent. Okay, so let's do it. We know pressure of a solution is directly proportional to the mole fraction of the solvent, because solute is non-volatile, right? So from there I can write pressure of the solution is basically equals to K any constant into mole fraction of solvent. Okay, so if I take K equals to P naught, so in that case it should be PS equals to P naught into mole fraction of the solvent, right? Okay, now what we can write? Delta P. What is delta P? Delta P is basically equals to P naught minus PS, right? So now here what we are going to do, let's say this is my equation number 1. From equation 1 I am going to put the value of PS here. So delta P equals to P naught minus P naught of mole fraction of solvent. Okay, just replacing the PS here. Okay, so now what I can do, I can take P naught as a common, so P naught into 1 minus mole fraction of solvent, right? From there if I continue, then it should be delta P equals to P naught. See, 1 minus mole fraction of solvent will give you the mole fraction of solute, right? Mole fraction of solute, right? So now from here what I can do, delta P by P naught is basically mole fraction of solute. Okay, so from here I can write P naught minus PS divided by P naught is basically equals to mole fraction of solute. So that is nothing but the relative lowering of vapor pressure. Okay, so this is what they are asking to derive you. Okay, I guess it's clear. Let's proceed further. Okay, so now they are asking draw a suitable labeled diagram to express the relationship for ideal solution of A and B between vapor pressure and mole fraction of the component at constant temperature. Basically they are asking to draw the diagram that is for the ideal solution in accordance to the Raoult's law. Okay, so here you can see vapor pressure versus mole fraction like this. If you join this intercept, you will get the total pressure. Okay, that's it. Let's proceed. Here you can see ideal solution, right? So ideal solution for this case, it will be equal to P naught A of XA and delta H mix, it should be equals to 0, and delta V mix, it should be equals to 0. Okay, non-ideal solution with positive deviation, so total pressure should be positive, right? More. So P naught A of XA, delta H mix should be positive and delta V mix should be positive as well. Okay, non-ideal solution with negative deviation, it should be this P naught of A XA, delta H mix should be negative and delta V mix should be negative as well. Okay, I guess it's clear. Let's proceed further. Give the difference between ideal and non-ideal solution. I guess you can do it. It obeys Raoult's law. It doesn't obey Raoult's law. Delta H, delta V, you can make V mix. You can mention about interaction. You can mention for ideal solution the interactions are same even after mixing. But in non-ideal solution the interaction after mixing changes. Let's proceed. Okay, differentiate between the types of non-ideal solution. One is positive deviation, another one is negative deviation. So along with example, you can take any 3 or any 2 in accordance to the marks, because it is a 3-marker question. You can take 3, okay, and you can go ahead. So yeah, let's proceed. Differentiate between maximum and minimum boiling azeotrope. So maximum boiling azeotrope shows negative deviation of Raoult's law, and minimum boiling azeotrope, they shows positive deviation of Raoult's law. Now for this case, for maximum boiling azeotrope, they boil at higher temperature than that of the usual boiling temperature of each component, right? And for minimum boiling azeotrope, they boil at low temperature than that of the each component expected boiling point. Example you can mention. Okay, let's pause it. Colligative properties, you can show that the relative lowering of vapor pressure for a solution is equals to the mole fraction of the solute when solvent alone is volatile. Already we did the derivation, you can just check out from here as well, or that derivation is also okay. Proceed further. Okay, show graphically how the vapor pressure of a solvent and a solution of a non-volatile solute change with temperature. Show on this graph the boiling points of the solvent and the solution, which is higher, and give reason. Okay, so for this case, this is nothing but the elevation in boiling point graph. So basically what happens whenever you are putting non-volatile solute in volatile solvent, there occurs elevation in boiling point. So usually in normal case you can see the solvent was boiling at this temperature TB0, you can see, but after the solute being added, it will boil at TB. Okay, and this particular difference is basically called as delta TB. Okay, so this is the entire thing. So boiling point basically increases. So elevation of boiling point, it is something that we observe here. Okay, I guess it's clear. Let's proceed further. What is semi-permeable membrane? Give an example of each for natural and synthetic semi-permeable membrane. So semi-permeable membrane is a membrane that allows only the solvent molecule very selectively, okay, to pass through it during the osmosis process. Okay, and example natural, you can take the example of animal bladder, and for the synthetic you can take cellophane paper, right? Let's proceed. Explain the desalination of water by reverse osmosis. Name the semi-permeable membrane used in it. So reverse osmosis is basically used in desalination of water. What actually we do here, in the salt water we give the pressure more than that of the osmotic pressure. As a result of this, solvent from the high concentration zone through the semi-permeable membrane, it comes to the fresh water zone where the concentration is low, okay, and we collect the pure water. Okay, so this is basically the reverse osmosis process that we use in the desalination mechanism. Okay, and here the membrane that we use, that is cellulose acetate. Okay, let's proceed. Okay, abnormal molecular mass. Why do electrolytes show abnormal molecular masses? Name the factors responsible for the abnormality. So basically they shows abnormal molecular masses because of two things: association or dissociation. Okay, so the factors responsible, definitely at first let me just discuss about the association. So sometimes what happens, because of the intermolecular hydrogen bonding, two molecule they gets attached, let's say dimerization of benzoic acid, right? So because of the hydrogen bonding only, so this is the association. Okay, so as a result of this, colligative properties will be observed. Then dissociation, let's say I'm taking one salt that will be dissociated, let's say aluminium sulfate, KCl, they will be dissociated into ions, right? So as a result of this, you can see more number of particles will be there. Okay, so molecular mass will be lower because they are dissociating into ions. I guess it's clear to you. Let's proceed. Okay, based on their nature of the compounds, assume that the compound will undergo either 100% association or 100% dissociation. Compare these compounds with a Van 't Hoff factor value. Okay, let's proceed. What we have to do here, we just have to break them in ions. So for K2SO4, 2K plus SO4, 2 minus. How many ions? Count. Total 2 plus 1, 3. Right? So here I am getting 3. Means 6. Okay. For NaCl if you break down, that's going to be Na plus Cl minus. It's going to be 2. Right? FeCl3, if you break down, same number of ions you will get for the K3 FeCl6 as well. So that's going to be Fe3 plus 3Cl minus. So how many ions you are getting? You are getting 4 ions out of it. So aluminium sulfate, let's break down for this case. 2Al3 plus 3SO4, 2 minus, how many ions? For this case you are getting 5 ions. Acetic acid and benzene, they will dimerize. Okay, so for dimerization we will get half. I'm directly writing it, we will get half. Urea and glucose, they will not dissociate, hence 1. Okay, so let me just point it properly. This is going to be 6, this is going to be 2, right, means 3. This is going to be 4, okay, this is going to be 2, and this is going to be 1, this is going to be 5. Okay, I guess this is clear now. Let's proceed further. Okay, give reason. This is reason based question from the solubility. First, aquatic animals are more comfortable in cold water than that of in warm water. What the reason behind it is, in cold water, because if you see the relation between temperature and solubility, they are inversely proportional. If you decrease the temperature, solubility will increase. So in cold water there will be more dissolved oxygen, and that is more beneficial for the aquatic animal. They will survive in a better way, right? This is the first case. Next, liquid ammonia bottle first cooled in ice before opening it. So basically what happens, ammonia in high pressure at room temperature, what happens, it is having high pressure at room temperature, right? Ammonia, they are having high pressure because it's very volatile, right? So if you cool it down, then what happens, the vapor pressure reduces, right? If the vapor pressure reduces, then whenever you are just opening the knob, it prevents the sudden exposure of ammonia gas, okay, sudden escape of the ammonia gas. Okay, that's it. Next, dissolution of some solid compounds is exothermic, while that of some other is endothermic. It is basically, in case you are having hydration energy greater than that of the lattice energy, then your process is exothermic, and if your hydration energy is less than that of the lattice energy, your process will be endothermic. That's it. Okay, so it is completely dependent upon the relative magnitude of the lattice enthalpy. Okay, lattice enthalpy and hydration enthalpy. Okay, I guess it's clear to you. Let's proceed. Okay, next question, the vapor pressure of a liquid is constant at constant temperature. So why? Because the vapor pressure, definitely it's constant at the constant temperature. Vapor pressure is constant of a liquid is constant at constant temperature. Why? Because an equilibrium is established in that temperature. Okay, so the rate of evaporation from the surface itself, from the surface of a liquid, evaporation takes place of that particular liquid, right? So rate of evaporation becomes equals to the rate of condensation. The rate in which it is going to the vapor phase, in the same rate it is coming back to the liquid phase at a particular temperature. That's the reason it is constant. Next, the vapor pressure of a solution of a non-volatile solute in a given solvent is less than that of a pure solvent. Okay, so what basically happening, whenever a non-volatile solute you are adding in a solvent, volatile solvent, then the non-volatile solute molecule, they gets accommodated on the surface area of the solvent. Okay, so vaporization takes place from the surface, right? If the surface is blocked by the non-volatile solute, then how it will come out? How it will get evaporated? Not possible. So as a result of this, vapor pressure decreases. Okay, vapor pressure is less, right, than that of the pure solvent. I guess it's clear. Let's proceed. Okay, an increase in temperature observed on mixing chloroform with acetone. So what basically happens? Definitely because of the hydrogen bond that will form. Okay, so intermolecular hydrogen bond forms in between the acetone oxygen and chloroform hydrogen that releases some sort of it. As a result of this, you will see some exothermic reaction. Okay, next, mixture of ethanol and acetone shows positive deviation from Raoult's law. So ethanol individually, it is having the hydrogen bonding, intermolecular hydrogen bonding, and acetone is having dipole-dipole interaction, right? So now what you are doing, you are mixing ethanol and acetone. So in between two ethanol molecule where hydrogen bonding was taking place, now acetone is coming in between. right? So hydrogen bonding will be disturbed, completely disturbed, right? So this is basically AB interaction, means ethanol and acetone interaction is weak, that is nothing but the positive deviation. Okay, next, pure ethyl chloride cannot be obtained from rectified spirit even by fractional distillation, because in this particular percentage, that 95.4% alcohol, in this particular percentage when they are present with water, then it forms the azeotropic mixture. Okay, and azeotropic mixtures cannot be separated using the fractional distillation method because they boils at the same temperature. Okay, let's proceed. Okay, ocean do not freeze, okay, because a large amount of salt, it is actually dissolved in the sea water. Because of that, the freezing point of water decreases a lot. Okay, as a result of this, it usually doesn't freeze. Okay, next, water stops boiling when sugar is added to boiling water. So again the same reason, if sugar is added, then it increases the boiling point of the water, elevation in boiling point takes place, right? So that's the reason that solution boils, means sugar water solution, it boils at higher temperature. Okay, next, the freezing point of a solvent is lowered on dissolving a non-volatile solute in it. Again the same thing, the freezing point is lowered when any kind of non-volatile solute is added to it, just because the vapor pressure decreases. Okay, like as the vapor pressure decreases, the equilibrium between the solid and liquid, that is achieved in lower temperature, right? So that is called the freezing point depression, right? So that we observe as a colligative property. I guess it's clear to you. You can see the answer from here as well. Let's proceed. Okay, while making ice cream in metal or plastic cones, the ice cream seller puts a mixture of ice and common salt around the cones and not ice alone. Okay, what's the reason behind it? Okay, so again the same thing, just to lower the freezing point. Okay, whenever you are mixing a non-volatile solute, that is your salt, okay, so the freezing point, okay, will decrease, right? Depression of freezing point, right? So as a result of this, it will be colder than that of the 0 degree Celsius. The ice will be colder than that of the mixture, not ice, the mixture of that salt and water, it will be colder than that of the 0 degree Celsius, right? So that's the reason. Next, when fruit and vegetables that are dried are placed in water, they slowly swell and return to the original form. This is just because of the osmosis, okay, through the semi-permeable membrane, the solution enters into that particular thing, that's why. Next, cutting onion taken from the fridge is more comfortable than cutting onion lying at room temperature. I would rather do that. Why? Because why it is more comfortable? Because it reduces the volatility of the chemicals, because the temperature is low, right? The temperature is low. As a result of this, the volatility of the chemicals that is present over there, majorly sulfur, okay, that causes the eye irritation. So they reduces the volatility. As a result of this, you will not get eye irritation. Okay, let's proceed. This is a diagram based question. For this graph, answer the following questions. What type of non-ideal solution shows such behavior? You can see this dotted line represents the ideal behavior. As you can see, it's towards a positive end. You can say it's a positive deviation. And next, give example for such type of non-ideal solution. Ethanol and acetone, you can take the example. Next, what type of azeotrope will the mixture of A and B form? So this is basically the positive deviation of Raoult's law. They will show minimum boiling azeotrope, right? Let's proceed. What is azeotropic mixture? Give example. What are the different types of azeotropic mixture? Explain with example. What are difference between minimum boiling azeotropes and maximum boiling azeotropes? Fine. So What are azeotropics mixture? They are basically the mixture of two or more substituents. They boils at a constant temperature. And one more thing that you can also mention, they have same composition in the liquid and the vapor phase as well. Okay, so you can take the example of the nitric acid and water, 68% nitric acid and 32% water. In that percentage ratio only, they will make the azeotrope. And next question was different type of mixture. Okay, different type, you can take the maximum boiling azeotrope and minimum boiling azeotrope. Now, what are the difference between minimum boiling azeotrope and maximum boiling azeotrope? That you can take, we already gave this over there. The difference, you can take that it will show minimum, negative deviation in Raoult's law, another one is positive deviation in Raoult's law, and when in which temperature they boils, we can give the example, already we have discussed. Okay, next, okay, so let's proceed further. Fine, we will proceed with the numerical problem now. Here you can see the first question, calculate the mole fraction of benzene and carbon tetrachloride in a solution made by dissolving 20 gram of benzene in 80 gram of carbon tetrachloride. Okay, let's do it. So number of moles of benzene, let's calculate at first. So number of moles of C6H6, let's calculate. So that's going to be 20 divided by 78. So almost it will come up to be something like 0.25, I guess. Okay, next, number of moles of CCl4. If I calculate this, it should come up to be 80 divided by molecular weight of CCl4 is 154. From here what I can get is 0.51, I guess. Okay, so now from here if I calculate the mole fraction of C6H6, so from here how I should do it, that is 0.25 divided by 0.25 plus 0.51, right? So if you calculate this, your answer will come up to be something like 0.33. Okay, and similarly mole fraction of CCl4, if you calculate 1 minus 0.33, that's going to be 0.67. Okay, I guess this is clear. It's directly, you just have to find out the mole fraction. Okay, let's proceed. The mole fraction of helium in a saturated solution at 20 degree Celsius is given. Find the pressure of helium, the solution of the above solution, Henry's constant is given. Okay, so here pressure of helium, it is basically what we can do is kH into X, right? Okay, so here you can see this is the Henry's law. So Henry's constant, kH into mole fraction of helium, right? So simply we can do it, 144.97 into 1.2 into 10 power minus 6. Okay, so from here if you calculate further, you will get 1.74 into 10 power minus 4. This. Further if you convert, it should be 0.174 bar only. Okay, that's it. I guess it's clear. Let's proceed further. The boiling point of benzene, this is a very important question actually. The boiling point of benzene is 353.23 Kelvin when 1.80 gram of a non-volatile, non-ionizable solute was dissolved in 90 gram of benzene. The boiling point raised to 354.11 Kelvin. Calculate the molar mass of the solute. Okay, so this is also a direct formula you can apply, that is elevation of boiling point. At first delta TB let me calculate, that is TB minus TB naught, right? So TB is given as 354.11 minus 353.23 Kelvin, right? So if you do this, it should come up to be 0.88 Kelvin, right? Now if you just put the formula, delta TB is basically equals to I into KB into M. Now further if you do, I value will be 1 because benzene is non-ionizable, right? So if I write KB, from this I can get weight of the solute divided by molecular weight of the solute into weight of the solvent into 1000, right? So from there your M2 will come up to be something like KB into W2 into 1000 divided by delta TB into W1. Okay, so now what I will do, I will just substitute the value here. So if I substitute, M2 is going to be delta TB we are getting as okay, KB at first 2.53 into weight, how much it is given, 1.80 into 1000 divided by 0.88 into 90 gram, right? So now if you calculate this, your answer will be 57.5 gram per mole. Okay, I guess it's clear to you. Let's proceed further. Okay, let's proceed. 1 gram of non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.4 Kelvin. Find the molar mass of the solute. So again the same approach we will proceed with. So delta TF is basically equals to KF into M, right? From there M2 we can write in the same way. Again you can see this is a non-electrolyte, so I value will be 1, right? So it should be KF into W2 into 1000 divided by delta TF into W1, right? So now if you put the thing, that is 5.12 into 1 gram into 1000 divided by 0.4 into 50. So if you calculate this, your answer will come. Okay, this is 256 gram per mole. Okay, I guess this is clear to you. Let's proceed. Okay, so we should proceed with some model paper questions. Let's start. Next, here you can see it's a diagram based question. Given below is the sketch of a plant for carrying out the process. Name the process. That is a reverse osmosis definitely, or better to say it is a desalination of water. Okay, name the process occurring in the given plant, means what's going on inside the plant. It's actually reverse osmosis is going on, right? Now name any one SPM, means semi-permeable membrane, which can be used in this plant. We can use cellulose acetate for the desalination. So reverse osmosis in bracket you can write desalination as well. Okay, one practical use already it is given as a question, so desalination of seawater you can mention. Okay, I guess it's clear. Let's proceed. Okay, name the concentration term which is commonly used in medicine and pharmacy. Write the definition and mathematical equation for the concentration term. So weight by volume percentage, this is something that we used for the pharmaceutical purpose. So how we should do it? Weight by volume percentage can be defined as weight of solute present in total volume of solution into 100. Okay, that's it. I guess it's clear. Let's proceed further. Write the reasons to justify the osmotic pressure method. Osmotic pressure method has the advantage over the other colligative methods for the measurement of the molar mass and macromolecules. So here comes three different reasons. You can see high sensitivity of the macromolecules. Okay, so as you can see, large molecules like protein, polymer, like whenever other colligative property like boiling point you are varying, freezing point you are varying, it's very difficult to measure the change at that particular variation of temperature because they are very much sensitive. Okay, because you need very dilute solution. Okay, means that's the reason in osmotic pressure method you can do the molar mass method, you can find out the molar mass in very diluted solution. So you can proceed with the osmotic pressure method. Next is room temperature measurement preserves the molecule. Sometimes in high temperature or low temperature, as you are varying the temperature, they can denature, right? They can break down, right? So that's the reason osmotic pressure method is more applicable because it can be done in the room temperature. Next, use of molarity, simplify the calculation. Okay, I guess this thing is clear to you. Let's proceed further. Okay, here comes a few questions, numerical problem we will discuss, that is from the model papers. Okay, first question, Henry's constant for the molality of methane in benzene at 298 Kelvin is given. Okay, calculate the mole fraction of methane in benzene at 298 under 760 mm of Hg. Fine. So let's proceed. At first we will see what is given to us. Okay, so let's proceed with the problem. So partial pressure of CH4 is basically equals to KH into mole fraction of CH4. Mole fraction of CH4 is something that we have to calculate, right? So that is basically equals to pressure of CH4 divided by KH. Okay, now simply just put the value. Pressure of CH4, it's definitely going to be 760 mm of Hg. Okay, divided by what is KH here? 4.27 into 10 power 5 mm of Hg. Okay, so if you calculate this, your answer will come up to be something 0.00178. That is the mole fraction of methane. Okay, I guess this is clear to you. Let's proceed further. Calculate the osmotic pressure in Pascal exerted by a solution prepared by dissolving 0.925 gram of polymer of molar mass this in 500 ml of water at 37 degrees Celsius. Okay, fine. Let's proceed. Here at first, see, pi equals to CRT. Osmotic pressure you have to find out. So this formula I need. So C I can write it in the form of N by V, right? N by V into RT. So I need to find out the N, right? So N is going to be equals to, see how much amount is given, 0.925 divided by 18500 gram. Okay, one more zero is there, gram per mole. We will do the calculation later. Okay, so pi is going to be, let's write all together everything, 0.925 gram divided by 18500 gram per mole. Okay, into how much volume is given, 500 ml. Okay, let's convert it into liter. If you convert it into liter, it should be 0.5 liter, right? It should be 0.5 liter. Fine. Next, here we will put the value of R, that is 8.314 into 10 cube Pascal liter Kelvin inverse, okay, into T T is basically 37 degrees Celsius. 37 degrees Celsius we have to convert it into Kelvin. So it will come up to be something 310 Kelvin. Everything here will be cancelled out. If you calculate this, your answer will come up to be something like 25.77 Pascal. Okay, so this is the answer. I guess you understood this. Let's proceed. Okay, so here you can see if solution obeys Raoult's law for all concentration, its vapor pressure would vary linearly from 0 to vapor pressure of pure solvent as shown in graph. Calculate the value of X. Okay, fine. So how I should calculate? It's very easy basically. P equals to P naught of solvent into mole fraction of solvent, right? So from here what I can do is, X value is this, right? This is my X, okay, vapor pressure, right? So this is going to be P naught will be how much? This is for the vapor pressure. In a normal case it should be atmospheric pressure, right? 1.013 bar, okay, into X value we can put from the graph itself, that is 0.4. Okay, so if you calculate this, it should come 0.4052 bar. That's it. This is your answer. Okay, so here the main thing is you just have to write down this atmospheric pressure by yourself. Otherwise it's a very simple numerical. Okay, I guess this is clear to you. Let's proceed further. Okay, calculate the mass of a non-volatile solute which should be dissolved in 114 gram octane to reduce its vapor pressure to 80%. Okay, let's do it. First, molecular weight of octane, if I do it, C8H18, right? So from here if I calculate 8 into 12 plus 18 into 1, so 114 I will get, right? 114 gram per mole. That is a molecular weight. Next, number of moles, let's calculate. Given weight by molecular weight. So 114 gram is also given, divided by 114 gram per mole, right? So from here I am getting 1 mole, right? So now what I have to do, relative lowering of vapor pressure formula I can apply. PS by P naught is equals to mole fraction, right? So as you can see, they are saying 80%, right? 80% of the pure solvent, right? It reduces its vapor pressure to 80%. So from here I can write P naught equals to 80% means, sorry, not P naught equals to, PS we can calculate, that is 80% of P naught, right? So from here 0.8 of P naught, that I can replace here, that is 0.8 of P naught divided by P naught equals to X2. Okay, so now if you just calculate X2 from this case, let me just simplify for you people. P naught I will cancel out. Okay, X2 will come as 0.2, right? 1 minus 0.8, that is 0.2. I guess up to this step it is clear to you. Okay, now we can calculate the number of moles. How? Because mole fraction X2 is going to be N2 divided by N1 plus N2, right? X2 we know that is 0.2 and N2 we have to find out, right? N2 divided by what is N1, that is 1 mole, right? Plus N2, we have to calculate N2, right? So 0.2 into 1 plus N2 will be equals to N2. From there, if you further calculate 0.2 plus 0.2 into N2 equals to N2. Okay. From here, if I do it, if it goes there, 0.8 of N2 will be equals to 0.2. From here, N2 value will come up to be something 0.25 mole. Okay. So now 0.25 mole, number of moles we got. Now easily we can get the weight, right? Mass we have to find out, right? So weight, how I should find out? That is weight equals to number of moles into molecular weight, right? Number of moles is how much? 0.25 into molecular weight is given as 40. So if you just calculate, it will come up to be something 10 gram. That is the answer. I guess you understood. First, we calculate the number of moles, that we replaced in the relative lowering of vapor pressure formula. From the relative lowering of vapor pressure, we got the mole fraction of the non-volatile solute. From the mole fraction, we got the number of moles of non-volatile solute, right? From the number of moles, we calculated the mass of the non-volatile solute. I guess this is clear. Let's proceed further. Here you can see, calculate the osmotic pressure of 0.5% weight by volume aqueous solution of sucrose at 300 Kelvin, and R value is given, molecular weight of sucrose is also given. So first we will calculate the number of moles. Okay, number of moles is basically 0.5. See, 0.5% weight by volume, by default it is saying 5 gram, I mean 0.5 gram of sucrose is present, right? So 0.5 divided by 342 gram per mole. This is gram. So if you calculate this, it will give you something almost equals to 0.00146 mole. Okay. So now volume, you can see volume by default I am having 100 ml, right? Means 0.1 liter. Okay. Now let's proceed with the formula. That is pi equals to N by V into RT. So N value is given, that you know, 0.00146 divided by 0.1 into R value is given here 0.0083 liter bar mole inverse, and temperature, that is 300 Kelvin, right? 300 Kelvin. Okay. So if you calculate this entire thing, your answer will come up to be something like 0.036384 bar, right? Okay. So yeah, I guess this is clear to you. Let's proceed further. Okay, so here is the end of the solution chapter. I guess whatever the question we covered, it will be more than enough for you. Okay, because we have covered a little bit PYQ, question bank questions and model paper. Okay, so yeah, that will be more than enough for the solution chapter. And for the MCQ part, please refer the all MCQ video that I already uploaded. Okay, let's proceed with the electrochemistry chapter. Okay, so first question, first we will recapitulate at first. So you can see E cell formula, E cathode minus E anode. This is the Nernst equation. Okay, this is the delta G and Nernst equation, I mean E0 cell relation. This is delta G and equilibrium constant relation. This is E0 cell and equilibrium constant relation. Okay, here comes the different terminologies along with their definitions and units. It's very important. Okay, just with a glance, just revise. Next, Faraday's law, this is the formula. Second law, this is the formula. resistance, that is the formula, resistivity, cell constant, conductance, conductivity, molar conductance. Okay, that's enough. This much formula you have to remember to proceed with the chapter. Okay, okay, it is from the electrochemical cell. 3-marker question. What is the role of salt bridge in connecting anode and cathode or two half cell? So first, it maintains the electrical neutrality both the sides, it prevents the accumulation of charges in the half cell, and it prevents the liquid-liquid junction potential formation. Okay, let's proceed. What is a salt bridge? And next question, what happens when a salt bridge is removed? Next, why KCl is used in the preparation of salt bridge? So here you can see salt bridge is basically a U-shaped glass tube that is filled with a agar-agar gel that contains different salt like KCl, KNO3, NH4NO3, this type of thing. Okay, this is salt bridge. Next question, what happens to the cell if it is removed, right? So if the salt bridge is removed, then there will be no current flow, hence potential will drop to the zero because the circuit is not yet completed, right? Next, why KCl is used? KCl is used because we choose those salt for those cases the cations and anions have the they have the same type of mobility or they have same velocity, okay, or sometimes we call it as transport number. Okay, they have almost same transport number, that's the reason we choose this type of salts. Okay, let's proceed. What is the standard cell potential of a Daniell cell? That is definitely 1.1 volt. Next, write the half cell reaction occurs in the Daniell cell. So anode reaction and cathode reaction that we can write. So here you can see, if I write that, it's already given here. Okay, so Zn will be converted to Zn2 plus and 2 electron. That 2 electron will be taken by Cu2 plus and it will be converted to Cu. So overall, if you just see overall cell reaction, Zn plus Cu2 plus will be converted to Zn2 plus plus Cu. That is the overall cell reaction. Okay, I guess it is clear to you. Next, what happens the cell potential when concentration of cathodic solution increases? So if the concentration increases of the cathodic solution, cell potential also increases. Okay, next, mention the direction of the current flow when the electrons are moving from anode to cathode during the working of galvanic cell. So if current moves from anode to cathode, if current moves from anode to cathode, definitely the flow of electron will be opposite to that of the electron flow. Okay, so they are saying that electrons are moving from anode to cathode, right? Electrons are moving from anode to cathode, so current will be moving from cathode to anode, like that. Okay, let's proceed. Write the symbolic notation of the Daniell cell. So here comes the symbolic notation. You can see Zn will be converted to Zn2 plus, it will be oxidized, and this is the salt bridge. Then Cu2 plus from the solution will be converted to Cu. That's it. Let's proceed. Okay, so let's proceed with the next problem. Here you can see a solution of CuSO4 is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at the cathode? Atomic mass of copper is given. Fine. So we can use Q equals to I into T. Q equals to I into T to find out the charge. So 1.5 ampere it is mentioned into 600 second, right? So that will give you 900 coulomb, right? So now Cu2 plus will take 2 electron and it will be converted to Cu. So number of moles of electron, if I want to find out, that is charge divided by Faraday. So 900 coulomb divided by 96500 coulomb per mole. Right, from here I will get 0.00932 mole. Okay, so now number of moles of Cu I have to find out, right? Number of moles of copper if I find out. So if 1 mole of Cu2 plus require 2 mole of electrons, so number of moles of Cu must be 0.00932 divided by 2. Okay, it should be 0.00464 mole. Okay, now from here I can find out the mass of copper, so that is basically 0.00464 mole into molecular weight, that is 63.5. Okay, if you calculate this, your answer will come as 0.2938 gram. Okay, I guess this is clear to you. Let's proceed further. How much electricity in terms of Faraday is required to produce 20 gram of calcium from molten calcium chloride? Fine. So calcium first, number 1, calcium 2 plus in molten, it will takes up 2 electron to give you calcium, right? So number of moles of calcium we can calculate, 20 gram is given, that is divided by 40 gram, that is the molecular weight of calcium, is going to be 0.5 mole. Okay, so number of moles of electron is going to be 0.5 into 2, that is 1 mole. So what is the charge of 1 mole of electron? That's going to be 1 Faraday. That is the answer. Okay, so 1 Faraday you need. Next, number 2. I am having Al2O3, means Al3 plus, right? So Al3 plus 3 electron will give you aluminium, right? From here, number of moles of aluminium, again in the same way we will do, 40 gram is given divided by 27. Okay, so if you do it, you will get something like 1.48. Okay, so now simply number of moles of electron in the same way you can calculate 1.4815, sorry, what I'm writing, 1.48 into 3 electron, right? So from here you will get something 4.44 Faraday. Okay, I guess this is clear to you. Let's proceed. Here we will discuss some model paper question. Okay, write the overall reaction of the nickel cadmium battery. Here you can see this is the anode reaction, cathode reaction, and overall cell reaction. Okay, next question, here you can see the cell is the cell in which the reaction occurs. Okay, let me just write it down for you. 2Fe3 plus 2I minus will give you 2Fe2 plus I2. This is the reaction. E0 value is given. Calculate log Kc. Fine. Let's do it. We can use directly the formula. E0 cell is basically equals to 0.0591 by N into log Kc. Right? So from here E0 cell I can calculate 0.236 equals to 0.0591 divided by 2 into log Kc. Right? So from there log Kc you can just calculate. Okay, your answer will come up to be something like 7.986. Okay, I guess this is clear to you. Let's proceed. Calculate the limiting molar conductivity of Cl minus ion by using the data lambda of calcium 2 plus and lambda m0 of CaCl2. Fine. So cold rush law we are going to apply here. So we know lambda m0 of CaCl2 is going to be lambda 0 of Ca2 plus 2 into lambda 0 of Cl minus, right? For this case, lambda 0 of Cl minus is going to be lambda m0 of CaCl2 minus lambda 0 of Ca2 plus divided by 2. So that's going to be, just put the value, 271.6 minus 119 divided by 2. Your answer is going to be something 76.3 Simon centimeter square mole inverse. I guess this is clear. Let's proceed. Okay, the limiting molar conductivity of CH3COH is given. Using the graph, given information, calculate the limiting molar conductivity of CH3COOK. Okay, so From the graph, I can get the limiting molar conductivity of KCl and HCl from the intercept, right? So, limiting molar conductivity of HCl, if I want to find out, it will be the intercept, that is 425 Simon centimeter square mole inverse, right? Now, for the lambda m0 for KCl, that is also given. So, that is basically in between 125 and 175. So, I can take 150 Simon centimeter square mole inverse, right? So, now what I can do, I can directly proceed with the formula, not formula, if I just break down. So, lambda 0 of CH3 COOK, that can be written as lambda 0 of CH3 COOH plus lambda 0 of KCl minus lambda 0 of HCl, right? So, this is how we can represent this. So, now what we have to do, we can just put the value over there. So, that is 390 plus KCl value is 150 minus 425. Okay, so your answer will be something 115 Simon centimeter square per mole. I guess this is clear to you. Let's proceed. Okay, mention 3 factors which decide the products of electrolysis. This thing we already discussed in the last few slides. You can just go through once. Proceed. What are the electrochemical cells? Name 2 types of cell, galvanic cell and electrolytic cell. Okay, proceed. One more numerical problem. A column containing 0.05 molar NaOH has an area of cross section 0.785 centimeter square. The length of 1 meter shows a resistance of 1.11 into 10 power 14 ohm. Calculate the molar conductivity of the solution. Okay, let's do it. So, here see, concentration is given, right? A is given as 0.785 centimeter square. I will convert it into meter square. So, 0.785 into 10 power minus 4 meter square. Right. Now, let's calculate G star, cell constant. It is L by A. So, 1 meter by 0.785 into 10 power minus 4 meter square. Okay, if you calculate this, it will come up to be something like 12740 meter inverse. Okay, so once you have the G star, you can calculate the kappa from here. If I want to calculate kappa, kappa is basically equals to G star by R. Okay, so G star value is 12740 meter inverse divided by 1.11 into 10 power 4 ohm, right? So, from here, if you calculate, kappa will come up to be something like 1.148 Simon per meter, right? Now, what you have to calculate? Molar conductivity, right? So, lambda m is basically going to be kappa by C into 1000. Right, just put the value over here, 1.148 into 1000 divided by 0.05. Okay, so if you just calculate this, your answer will come up to be something like 0.02296 Simon meter square per mole. Okay, I guess this is all right. You understood this. This is step number 1. You have to calculate the G star. Using G star, calculate kappa. Using kappa, calculate the molar conductivity. Okay, let's proceed further. Okay, for this case, what you have to do? Calculate the electromotive force of the cell. Assume the cell reaction at 25 degrees Celsius with the reaction this. Okay, we can simply use Nernst equation out of it. So, E cell equals to E0 cell minus 0.059 divided by N log Cu2 plus by Ag plus whole square, right? So, let's put the value 2.97 minus 0.059. Here number of electron exchange is 2. Log, let's put the value 0.25. Sorry. 0.25 divided by 10 power minus 3 whole square means 10 power minus 6. Okay, so if you just calculate this, I'm not going to the detailed calculation of it. I'm just directly telling you the answer. You can calculate log nicely. So 2.811, wait, yes, 2.811 is going to be the answer. Okay, I guess this is clear. Simple Nernst equation application. Okay, let's proceed. Okay, we will proceed with the chemical kinetics now. Okay, for the reaction H2 plus I2 will give 2HI. Draw the diagram showing the plot of potential energy versus reaction coordinate to the to explain the role of activated complex in the reaction. So here you can see H2 plus I2, they will react and they have to cross the activation energy barrier. At the top of the peak, you will see the activated complex is generated where it is neither the reactant nor the product. That is called transition state. After crossing the activated complex, it will come up to be the product. Let's proceed. Mention 3 factors that affect the rate of a chemical reaction. So these are the factors. You can see, you can take concentration, temperature or catalyst. Proceed. Okay, one more numerical. The first order rate constant at 600 Kelvin is 2 into 10 power minus 5. And the energy of activation is 209.8 kilojoule per mole. Okay, calculate the rate constant at 700. So Arrhenius equation you have to use here. Let's proceed. So log K2 by K1 equals to EA by 2.303 R into T1 into T2. So T2 minus T1 here. Okay, so let's proceed. K2 you have to find out, K1 we can put from the question itself, that is 2 into 10 power minus 5, right? Equals to EA value, you can see it's given in kilojoule per mole. We will convert it to joule. So 209,800 joule per mole divided by 2.303 into 8.314 in 8.314 joule per mole per Kelvin, right? Into T1 and T2 value if I put here 600 into 700, here 700 minus 600, 1 by K. So everything will be cancelled out here, you can see. So log K2 by 2 into 10 power minus 5 is going to be something 209,800 divided by 2.303 into 8.314 into 100 by 421,234. Okay, this is the thing you will get. So on being simplified, you will get something like this. This side if you calculate completely, you will get log K2 by 2 into 10 power minus 5, you will get this side 2.6. Further if I calculate, I will do anti-log. K2 by 2 into 10 power minus 5 equals to 10 power 2.6. Okay, so now what we can do is K2 equals to 2 into 10 power minus 5 into 10 power 2.6. So if you just calculate this, it will come up to be something like 8.1 into 10 power minus 3 second inverse. Okay, I guess this is clear. Okay, the full calculation I showed here, I guess it's clear for you. Let's proceed. Okay, this is a MCQ based question, very important question from the model paper. The reaction 2NH3 gives N2 plus 3H2. The rate is going to be a zero order reaction. Why? Because the dissociation of the gas or decomposition of the gas is going on a metal surface. Let's proceed. Write 2 differences between order and molecularity. Here you can see so many differences are there. Any 2 you can pick and you can write it down. Let's proceed What is meant by chemical kinetics? Give any two importance. Chemical kinetics is basically a branch of chemistry that deals with the rate of a chemical reaction, and definitely different factors that affects the rate. Okay, it helps us to determine the speed of or rate of a reaction, and also like how the rates can be altered. Proceed. Next, one more numerical. The rate of a reaction quadruples when the temperature changes from 293 to 313 Kelvin. Calculate the energy of activation. Again, this is a type of Arrhenius equation you have to apply here. Let's proceed. Okay, so log K2, we can see the rate is quadrupled, right? So from here I can tell you K2 is basically 4 into K1. I am directly putting here 4 K1 divided by K1 equals to EA by 8.314 into 2.303 313 minus 293 divided by 293 into 313. Okay, so if you calculate this further, this is going to be log 2 square is equals to EA by 8.314 into 2.303. Here you will get 20 divided by 293 into 313. Now simply if you just calculate this thing, log 2 value is 0.301. EA is going to be 2 into 0.301 into 8.314 into 2.303 into 293 into 313 divided by 20. Okay, so this is the calculation. If you do this calculation, your answer should come like 52.8 kilojoule per mole. Okay, be careful about doing this calculation. Okay, let's proceed. Yes, okay, so this is a very important problem actually. The C14 content of an ancient piece of wood was found to have 3/10 of that of living tree. Calculate the age of that piece of wood. Fine. We can use the first order equation, first order rate equation only. So because any radioactive decay will follow first order equation, first order kinetic. 303 divided by lambda. Lambda is called as decay constant. Log N0 by Nt. Right. So lambda we have to calculate because half life is given. You can see lambda equals to 0.693 divided by T half, right? T half is given as 5730. Fine. Now they are saying that Nt is equals to 3/10 of N0. So from here Nt by N0 I can get 3 by 10. Okay, let's put everything here. So T is going to be 2.303 divided by 0.693 into 5730 into log 10 by 3 because not by Nt, 10 by 3. Okay, so now if you just simply calculate, I am not showing the detailed calculation here. You can break down log 10 minus log 3. Okay, and you can put the value of log 3. Okay, if you calculate this, you will answer, your answer will be 9957 years. That is the answer. I guess this is clear to you. Yeah, let's proceed. Okay, for this particular problem, ROR, rate of reaction, is basically equals to minus 1 by 2 dA by dt equals to minus 1 by 3 dB by dt equals to minus 2 dC by dt. If you just multiply these two with everything, it will be something like minus dA by dt equals to minus 2 by 3 dB by dt equals to minus 4 dC by dt. So option A is going to be the correct one. I guess this is clear. Let's proceed. Derive the integrated rate equation for the zero order reaction. Okay, let's do it. So A gives you P. Let's say this is my equation. Okay, so rate in accordance to the differential rate equation, we can write minus dA by dt. This is your equation number 1. Next, R equals to, from the rate law you can write K into A power 0. Let it be your equation number 2. Equating these two, you will get dA by dt equals to minus K into A power 0. A power 0 means you know it's 1. Right? So from here, if I just integrate by arranging a little bit, dA equals to minus K into integration of dt. So when t equals to 0, A is A0. Okay, when t equals to t, it is AT. Okay, now let's put the limit after doing the integration. So from here I will get AT minus A naught is basically equals to minus KT. From here K you will get A naught minus AT divided by T. That's it. Okay, I guess this is clear for you. Let's proceed. Okay, one more numerical problem here. You can see a first order reaction has rate constant this at 500 Kelvin, and at what temperature the rate constant becomes this, means T2 you have to calculate. Fine, let's do it. So log K2 by K1, let me directly write the, let me directly substitute the values, because already I have written this equation for multiple times. So log K2 value is 17.25. 17.25 into 10 power minus 4 divided by 2.3 into 10 power minus 5. Okay, equals to, EA value is given as kilojoule. We will convert it into joule. So 191478. Okay, divided by 2.303 into 8.314 into T2 you have to calculate, right? So 1 by 500 minus 1 by T2, that's it. So if you calculate these portion, you will get log 75, okay? So log 75 is basically equals to, if you calculate these portion, this, you will get 10,000. Okay, 10,000 point something, I am just simplifying it to 10,000, okay? Divided by, into 1 by 500 minus 1 by T2. Okay. Now log 75 if you calculate, you will get 1.87. Okay, equals to, if I just simplify, 10,000 by 500 Kelvin minus 10,000 by T2. So by simplifying, I am not going to further simplification, you can do this I guess from here. T2 you will get something 551.57 Kelvin. Okay, I guess this is clear to you. Let's proceed. Okay, a first order reaction has half-life 23 minutes. How much time will be needed for 30% completion of the reaction? Fine. So let's calculate K from the half-life, that is equals to 0.693 divided by 23. It's going to be something like 0.0301 minute inverse, right? Okay, now here you can see AT means after 30% completion you will get 70% left over of A naught, from here 0.7 of A naught, right? So if you just put it into the first order integrated rate equation, that is T equals to 2.303 divided by 0.0301 log A naught by 0.7 of A naught. Okay, just simplify this, everything will be cancelled out here, A naught will be cancelled out here. T, if you calculate further, you will get your answer as 11.84 minute. That is your answer. Okay, I guess this is clear to you. Let's proceed further. little bit we will do from question bank. Okay, again I am telling you this type of question I already solved. Initial rate method, develop 3 different equation and then solve it out for x and y, you will get it. Okay, let's proceed further. Okay, for a first order reaction, plot the graph of log R0 versus R versus time. Okay, so how you should do, you know, if I show you from this step, integration of d of a by a naught to at is equals to minus k into integration of t equals to 0 to t. Okay, if I show it from here, that is ln of at minus ln of a0 equals to minus kt. Fine. Now if I convert it to log and also alter the sign, I will get 2.303 log a naught by at. I altered the sign. Okay, a naught by at, here I am getting kt, right? So now if I just change the side, log a naught by at is basically equals to k by 2.303 into t plus I can write 0. So this is your y, right? This is your m, this is your x, this is your intercept. 0 intercept means it is passing through origin, right? So let's plot the graph. So I am having log a naught versus at at the x-axis. This is t, okay? It will pass through origin, and the slope value you can write from the equation itself, that is k by 2.303. I guess this is clear to you. Let's proceed. Okay, what happens to the half-life time of a first order reaction when the temperature is increased? So basically half-life of a reaction will decrease as the temperature is increased. Okay, why? Because temperature is directly proportional to rate constant. If you increase temperature, rate constant will increase, and half-life is inversely proportional to rate constant, and hence half-life will decrease. I guess it's clear. Let's proceed. This is the plot of Maxwell-Boltzmann curve, and this particular point after which the molecule will take part in the reaction, that is the activation energy. Okay, I guess this is clear. Let's proceed. Illustrate the graphically the effect of catalyst on activation energy. You have to draw this graph. You have to mention that initially the activation energy was this much, but after adding the catalyst, the dotted line represents the path on being added with the catalyst. So as you can see, activation energy will be reduced. Proceed. Graphically represent the Arrhenius equation. Here you can see ln k versus 1 by t we can represent, and slope we can calculate. From the slope we can calculate the energy of activation, because slope value is minus a by r. Okay, let's proceed. Derive integrated rate equation for the first order reaction. Okay, let's do it. A gives you the product. Okay, so from here r equals to minus dA by dt. This is your equation number 1. Next, r equals to, from the rate law, I can write k into a power 1. Okay, this is equation number 2. This 2 can be, if we equate equation 1 and 2, so minus dA by dt will be equals to k of a. If we rearrange and do the integration, you can do it in different step. So integration of d of a by a equals to minus k into integration of dt. So here it is a0 to at if I put the limit, and here it is t equals to 0 to t equals to t, right? So from here further I can move towards this. If I just do the integration, ln of at minus ln of a naught is equals to minus kt. If I just alter the sign and do the log, converting into log, so it will be 2.303 into log a naught by at is equals to kt. So yes, from here I can come up with k equals to 2.303 divided by t log of a naught by 80. This is the equation. Okay, I guess this is clear to you. Let's proceed. Okay, what is the effect of catalyst on the reaction with respect to activation energy? So positive catalyst, definitely it reduces the activation energy and it makes the reaction rate faster, and delta G, it has no role with the delta G. Okay, let's proceed. If a homologous catalytic reaction can take place through 3 alternative paths as depicted below, the catalytic efficiency of PQR. So definitely, as you can see, P is having more activation energy, right? So it will take more time, then Q, then R. So whenever I am using R as a catalyst, the reaction will be fastest. After that Q, then P. Okay, more numerical problem we will proceed with. In a chemical reaction, A plus B gives C plus D. The concentration of the reactant A alone is increased by 2 times. The rate is increased by 4 times. Okay, one by one we are going to write. Here also you have to develop the equation. So let's say R1. R1 is equals to K into R, normal R also you can take actually, A power X into B power Y. This is your equation number 1. Okay, so first condition what they are saying, reactant K they are doubling 2 times, they are doubling, right, and B they are keeping constant, the reaction rate will increase 4 times, so 4 of R. This is equation number 2. Another one they are saying that if concentration of both A and B increased by 2 times, so K into 2A power X, 2B power Y, right? This is equation number 3. Okay, the rate is 8 times. Okay. Okay. Now we have to solve this equation to get X and Y value. So what I can do is 3 divided by 2 I can do, 3 divided by 2. So here 8R divided by 4R is going to be 2A, K is also there, 2A power X into 2B power Y divided by K into 2A power X into B power Y, right? From here what you can get is 2 equals to 2 power Y. From here I can get Y equals to 1. Fine. Now solve for X. What I should do? I can do 2 divided by 1. If I do 2 divided by 1, so 4R divided by R is basically equals to K into 2A power X into B power Y divided by K into A power X into B power Y, right? From here I am getting 4 equals to 2 power X, so I can write X equals to 2, right? So overall order, if I want to write further, R equals to K into A power 2 B power 1. It is second order with respect to A and first order with respect to B. I guess this is clear to you. Let's proceed. Calculate the time in seconds for the decomposition of nitrogen pentoxide with which follows first order kinetics when concentration of N2O5 is dropped from 0.1 molar to 0.01 molar. Okay, it's very easy basically. First order kinetics we can use 2.303 divided by K into log A0 by 80, right? Everything just you have to put the value and calculate. 2.303 divided by 6.2 into 10 power minus 4, it's given already. Log, it started from 0.1 and it dropped to 0.01. So if you just simply calculate, you will get the answer. Okay, I'm just directly going to the answer. You will get as 3.7 into 10 cube second. Okay, I guess this is clear to you. Let's proceed. Okay, so for a first order reaction, show that the time required for 99% completion is twice the time required to the completion of 90% reaction. Fine, let's do it. So T of 90%, let's do, that is 2.303 divided by T log A0 is 100, 90% completed means 80 is 10. Right, from here I can write 2.303 by K into log 10. That's it. Next I can do, this is T of 90%. Okay, next I can do T of 99%. Okay, that is 2.303 divided by K log of A0 A0 by 0.01 basically, because 1 by 100, right, into A0. Okay, so if I further do this, T 99% will give you 2.303 by K into log 10 square. Okay, from here I can write T 99% is basically 2 times of 2.303 divided by K into log 10. Okay, so what is this? This is nothing but T90, right? So T99% is basically 2 times of T90%. Proved. Okay, I guess this is clear to you. Yeah, let's proceed. T half of a reaction is 10 minutes. For a first order reaction, what % of reactant remain unreacted at the end of 50 minutes? Okay, so number of half-life. Number of half-life, how I should get it is basically, let it be N. Okay, that is basically T by T half. Okay, total time is how much? End is 50 minutes, right? 50 divided by 10 minutes, that is 5. Okay, now fraction of the reactant. Fraction of reactant remaining after n half-life, there is a formula, it's going to be half power n, right? Half power n, remember this. Okay, so from there percentage how I should get, that is half of n, half power n into 100%. Okay, so let's put half power 5 into 100%. Okay, so from here we will get 1 by 32, right? 1 by 32 into 100%. So you will get here 3.125%. Okay, so this is the process. Let's proceed. Yes. Okay, the graph of log K versus 1 by T for reaction is linear with intercept 10 and slope given. Okay, calculate the frequency factor and the EA. Okay, so it is basically Arrhenius graph. Okay, Arrhenius graph value, I guess you know, if I just write down the equation, log K equals to log A minus EA by 2.303 R into 1 by T, right? So from here what they are asking, log A is given as 10. Log A is the intercept. Okay, it is given as 10. From here if I find out A, that is going to be 10 power 10. That's it. Okay, next slope. Calculate the frequency factor we have to calculate, and EA as well. Okay, so slope we are having from this straight line equation, slope we are having minus EA by 2.303 R. Slope value is given as minus 5.1 into 10 cube. So let's multiply into 2.303 into 8.314, that is equals to EA. So EA, your activation energy is going to be how much? It's going to be 97.650 kilojoule per mole. Okay, I guess it's clear to you. Yeah, let's proceed further. This is your frequency factor, this is your activation energy. Okay, let's proceed. Okay, so that's it. So here comes the end of the entire physical chemistry. So I guess you understood what type of problem can come and which formulas you have to focus for the numerical purpose. A lot of numericals we did here. If you do this, I guarantee 65 plus marks in your chemistry examination. So yes, without further delay, don't forget to like the session. If you have not subscribed, then please subscribe and share this video with your friends so that they can also get the benefits of this video. Thank you so much for watching. Hello my beautiful students, I know your PU2 examination is knocking the door, so at this moment you are looking for the most expected question that you are going to face in your examination. So yes, here I am going to cover the entire inorganic chemistry part that will include the D and F block elements and the coordination compounds. So all probable problems, MCQs that I am going to cover here. So without delay, let's get started with the first chapter, that is D and F block elements. So yes, here we will discuss a little bit model paper at first. So all the model paper, whatever the question came from the D and F block, we are going to cover at first, and then a little bit from the question bank, whatever the previous year question and a little bit important question, that also we are going to cover. So if you do this, I am assuring you it's going to be more than enough. So let's proceed. What are transition elements? Give an example. So as you can see, elements having partially filled d orbitals either in their ground state or in their common oxidation state. Okay, they are called as transition element. You can take the example of manganese. Okay, so let's proceed further. What is lanthanide contraction? Mention two consequences of it. That is basically gradual decrease in the atomic and ionic radii from lanthanum to lutetium. Right. So what are the consequences? The consequences you can include that it becomes very much difficult to separate the elements of 3D and 4D. So like zirconium and hafnium, from their ore it becomes difficult to separate zirconium and hafnium because of the same chemical and physical properties, right? Another one you can take, the basicity decreases from lanthanum to lutetium. Okay, let's proceed. Okay, so complete the equation. I can do it like chromite, right? 4FeCr2O4. That is chromite. Next here MnO2, if it is fused with KOH, I will get K2MnO4. K2MnO4, along with that definitely 2H2 I will get. Okay, now KMnO4, if it is decomposed, means if it is, you can see thermal decomposition, heat is given here, K2MnO4, along with that MnO2 you will get, and oxygen. Okay, give reason. Separation of lanthanides is difficult from their natural occurrence. Here I already told you, due to the lanthanide contraction, the atomic radii of zirconium and hafnium, it becomes almost similar. Okay, so they occur together. Okay, next, study of actinides are difficult. Why? Because first of all they are radioactive element. Next, their half-life are very short. Okay, so like you need more time to do the research on it, right? Next one is like they could be prepared in nanograms, right? So these are the things for what actinoids study is difficult. Let's proceed. Explain the preparation of potassium permanganate from MnO2 with balanced equation. Okay, so this is the potassium permanganate preparation. It's very important. Either dichromate or potassium permanganate preparation you can expect in your examination. Okay, so here what we will do, first we will fuse MnO2 with KOH, we will get K2MnO4. After that conversion, means it's a disproportionation type of reaction takes place. K2MnO4 will give you KMnO4 plus MnO2. Okay, so this is how you can get. Next, mention the gas evolved when KMnO4 is heated. So KMnO4, we already did this in the form of fill in the blanks. Here again, KMnO4, if it is heated, you will get K2MnO4 plus MnO2 plus oxygen gas. Okay, let's proceed. Considering the elements of 3D transition series, write the element which is first unable to form monoxide, that is scandium. Scandium is unable to form the monoxide because it always exists in +3 oxidation state. Next, having positive E0 value, that is copper +0.34 something. Okay. Next, a base element of Ziegler-Natta catalyst, that is Ti. Okay, Ti means titanium. Proceed. With respect to first transition element series, which element has highest second ionization enthalpy and lowest enthalpy of atomization? So definitely first answer is going to be copper. Why? Because copper, if you remove the first electron, 4s1 will be removed and it is having 3d10. So from 3d10, second electron removal becomes very difficult. So that's why second ionization enthalpy become high, and lowest enthalpy of atomization is because it is having zinc. Why? Because zinc has no unpaired electron. All the electrons are paired up. That's why. Let's proceed. Write the balanced chemical equation involved in the manufacture of potassium dichromate from the chromite ore. So first, as you know, you just have to heat FeCl2O4, that is a chromite, with Na2CO3. You will get sodium chromate. Sodium chromate on being treated with acid, you will get sodium dichromate. Sodium dichromate, you have to treat this with KCl. You will get K2Cr2O7. Let's proceed. Write the formula of the 3 different types of compounds formed when lanthanide reacts with carbon or heated with carbon. Okay, so we can get Ln3C, Ln2C3 and LnC2 type of compounds. Okay, let's proceed. Okay, this is from the question bank we are going to cover. Here, name the 3D series elements having maximum melting point and minimum melting point. Maximum melting point will be having chromium because of the presence of unpaired electron, and minimum is zinc because it has no unpaired electron. Proceed. Why do the transition element exhibit high enthalpies of atomization? So the reason is the number of unpaired electron. Okay, they have stronger interatomic interaction because of the presence of unpaired electron. As a result, their enthalpy of atomization, means to separate them into the individual atom, becomes very difficult. Let's proceed. The atomic sizes of iron, cobalt, nickel are nearly same. Why? Because iron, cobalt and nickel, their like increasing effective nuclear charge and poor shielding effect, they balance each other properly. Okay, that's the reason as you are moving from iron, nickel, definitely the nucleus will gain proton, nuclear pool will increase, but in the D shell the electrons will also be added, right? So they will counterbalance each other, and as a result of this, atomic radius becomes constant. Okay, let's proceed. Why manganese exhibit maximum oxidation of +7 only with oxide? So it's a very important question. So oxygen can form a very strong multiple bond with manganese. Okay, p-pi d-pi type of bonding they can form, that makes the entire compound very stable. Okay, so but here fluorine cannot make it. Just because it cannot stabilize the +7 oxidation state with the single bond only, right? That's the reason oxygen can do it. Proceed. Cu2 plus is more stable than that of Cu plus, because Cu2 plus has it's all about the ionization enthalpy. Okay, so the stability of Cu2 plus is more due to the much more negative hydration enthalpy. Whenever you are just dissolving that Cu2 plus into the water, the hydration enthalpy of Cu2 plus is more than that of Cu plus. Okay, so that compensate the ionization energy that is required to remove one electron from 3d10. Okay, that's the reason Cu2 plus is more stable. Let's proceed. Why is Cr2 plus reducing and Mn3 plus oxidizing when both have D4 configuration? So Cr2 plus is reducing because the configuration changes from D4 to D3. But Mn3 plus is oxidizing because the configuration changes from Mn3 plus to Mn2 plus, that is D5 configuration, right? Which has some half-filled stability, right? D3 has no stability, but D5 has extraordinarily symmetrical stability, right? Proceed. The E0 of M2 plus M value for the copper is positive. The reason, okay, so the reason is high enthalpy of atomization and low enthalpy of hydration. Okay, means a large amount of energy is required to convert the solid copper to Cu2 plus ion, right? And this particular thing will be counterbalanced by the hydration. Okay, so I guess you understood this. First of all, Cu2 plus ion needs to be prepared, right? And after that, Cu2 plus needs to be stabilized. So how it will be stabilized? By adding the extra hydration enthalpy. So this much energy you need, that's why plus 0.34. Let's proceed. Which is a stronger reducing agent, Cr2 plus or Fe2 plus, and why? Definitely Cr2 plus is going to be a very stronger reducing agent than that of Fe2 plus. Why? Because the configuration you see for Cr2 plus, it is changing from D4 to D3, okay, and D3 is getting stability because it is half filled T2G orbital, okay. T2G can have 6 electron maximum, so it is half filled T2G and hence it's more stable. Okay, let's proceed. Transition elements form colored compound. Give two reasons. First, it is a DD transition that I already explained. So unpaired electron should be there and partially filled d orbital should be there. It will undergo DD transition, right? As a result of this, you will see it will radiate the complementary color. Okay. Proceed. The transition metals and their compounds are known for their catalytic activity. Give two reasons. First reason is variable oxidation state. So many oxidation state they are having. Next, surface area. They provide a large surface area for the adsorption of the reactant molecule. Next, the presence of incompletely filled d orbital. It's very important. Okay. Next, it can form very stable intermediate compound. Okay, like vanadium pentoxide we can use in the contact process for the manufacture of H2SO4 just because of that. Okay, let's proceed. Okay, iron catalyzes the reaction between iodide and persulfate ions in the reaction. Explain the catalytic action. Okay, so here you can see if you just look at the reaction, you will understand iron 3 plus will at first react with I minus, okay, and it will form iron 2 plus and it will liberate I2. Further, this iron 2 plus will react with persulfate to give you the SO4 2 minus and iron 3 plus will be regenerated. So if you just look at the reaction, then you will understand. Okay, I guess it's clear. Let's proceed. Write the characteristics of the interstitial compounds. So interstitial compounds definitely they have very high melting points. Okay, they are chemically inert. They retain their metallic conductivity. Okay, proceed. What is the composition of mismetal and write one use of it. So this is the composition. 95% lanthanide should be there. Plus iron should be there almost 5% and the trace of sulfur, carbon, these things should be there. Okay, and mismetal is used in magnesium based alloy to produce bullets. Okay, shell and lighter flints. Okay, let's proceed. Draw the structure of dichromate ion. What is the value of bond angle in CrOCr? So this is a structure of dichromate ion. You can see the bond angle is 126 degree. Let's proceed. Give general characteristics of lanthanides. Okay, 3-marker question. It's definitely white metal, tarnished, and definitely it gets tarnished in air rapidly. Hardness increases with the atomic number. Next, they are good conductors of heat and electricity, and all lanthanide ion except La3 plus and Lu3 plus, they are colored both in solid state and in aqueous state as well. Okay, so I guess one more. Okay, lanthanide ion except F0 and F14 type, they are all paramagnetic. Clear? Proceed further. Okay, what is actinoid contraction? Actinoids show greater number of oxidation state and why? Okay, one by one let's discuss. First, actinoid contraction is same as that of the lanthanide contraction. Gradual decrease in the size of the atoms of actinides across the series. Okay, and next question, actinoids show greater number of oxidation state. Why? This is because the energy gap between 5F, 6D and one more 7S. Okay, comparable energies, very close by there. Okay, so removal of electrons are easy, that's why they show variable oxidation state, even more than that of lanthanoids. Last question, common oxidation state, it is +3. Let's proceed. Why cerium shows +4 oxidation state? Okay, so basically cerium shows +4 oxidation state. If you see the electronic configuration, then you will understand. Cerium +4 will get the xenon-like configuration, that's a noble gas. So to get the inert gas-like configuration, it shows +4 as an better oxidation state, best. Okay, next, what is the highest oxidation state shown by the actinoids? That is +7 can be exhibited, and name an element that shows highest oxidation number among the actinoids. Neptunium is one of the element that will show +7 oxidation state. Okay, let's proceed. Give any 3 general characteristics of actinoids. Here you can see definitely all of them are radioactive, silver color, highly reactive, okay, and paramagnetic in nature. What we can tell more? Slightly affected by the concentrated nitric acid owing to the formation of the protective oxide layers. Okay, so that is basically creates some passivity, right? And it can be highly affected by the hydrochloric acid. And oxocation they used to form, as you can see, neptunium with oxygen, NPO plus, it is oxocation. Okay, so I guess it's clear to you. Let's proceed. Lanthanoids and actinoids difference you can just go through from here, and you can just pick any 3 of them and you can just write it down. Okay, proceed. Study of actinoid element is difficult. Give 3 reasons. So first, I already told you, radioactive element half-life is very short and they can be prepared in nanograms. Let's proceed. Okay, so let's proceed further. Okay, so here we are ending for the D and F block element, and we are entering into the coordination compounds. So yes, let's proceed. State the postulate of Warner's coordination theory. You can see, you can just talk about the primary and secondary valency, which one is ionizable, what does it mean by secondary valency, that ligand used to satisfy that. Then you can mention about the the ions or group that bound by the secondary linkages, they have some special arrangement within it. Okay, there's many points you can mention. Let's proceed. FeSO4 solution mixed with NH4 whole twice SO4 solution is 1:1 molar ratio gives the test for Fe2+, but CuSO4 solution mixed with aqueous ammonia in 1:4 molar ratio does not give the test for CO2+, because for the first case it forms the more salt. Okay, more salt, when it dissociates, it gives the test for the Fe2+, because it dissociates Fe2+. Okay, but whenever CuSO4 is mixed with the solution, aqueous ammonia solution in 1:4, it makes a coordination compound, and Cu becomes a part of the coordination entity. That's why it is non-dissociable. So it doesn't give the test for Cu2+. You can just go through this. That's the thing I just told now. Okay. So this is the reason. Okay, let's proceed further. Okay, on the basis of the following observation made with aqueous solution, assign the secondary valencies to the metal. Okay, so one by one we will do. For the first case, number 1, here let me write number 1. Here I am getting 2 AgCl unit as a precipitation, means the compound should look like PD NH3 whole 4 outside Cl2, and here I will write the secondary valency. Okay, secondary valency for the first case is going to be 4. Second case if I draw it, you can see I am getting 2 unit of AgCl precipitation. So NiH2O whole 6 outside Cl2. This case it is 6 secondary valency. For 3, there is no AgCl precipitation, right? So you can do it like PtCl4 like this, okay, dot HCl. Okay, so for this case 2 HCl, I am getting 4, right, secondary valency. Next COCl3, I am getting 1 as a AgCl, okay. So CO here NH3 inside 2 Cl, outside 1 Cl. So for this case also I am getting 6. Next, okay, I am getting no AgCl precipitation for 5. So PT, here I am having NH3 whole twice Cl2, right? No precipitation, and hence you are getting here 4 as well. Okay, I guess this is clear to you. Let's proceed further. Explain the example of the following. Okay, so coordination entity, ligand and coordination number. Coordination entity means whenever the metal is connected to the ligand with the coordination bond, right, and that part is non-ionizable. Okay, and this is you can explain as coordination entity. Next is ligand. Ligand is basically electronically enriched species that donates the electron pair to the metal center. Next, coordination number. Coordination number is the number of ligands that is attached with the metal. Okay, so you can see here comes the full explanation of this. You can just go through. Let's proceed. Okay, let's proceed. Explain with 2 examples each of the following coordination polyhedron. What is coordination polyhedron? It is basically the special arrangement that ligands around the central atom. Okay, this is called coordination polyhedron. Okay, you can just take the example of, let's say, nickel tetracarbonyl compound. Okay, next you can see homoleptic complex. If in the coordination entity you are having same type of ligand, it is called homoleptic complex. Next is heteroleptic complex. If you in the coordination entity you are having 2 different type of ligand, then you can just call it heteroleptic complex. Examples are given here. Okay, let's proceed. What is meant by unidentate, bidentate and ambidentate ligands? Give 2 examples. So unidentate ligand means it has only one donor atom to form only one coordinate bond, like Cl minus NH3, like this. Bidentate means it has 2 donor atom, okay, like oxalate. Okay, next ambidentate, it has ambidentate, it has 2 donor side but donates from one side at a time. Okay, like Cn minus, I can take the example, SCN minus, I can take the example. It has 2 donor side but it donates from one end at a time. Okay, let's proceed. What are chelating ligands? So chelating ligands, you can see when a di or polydentate ligands, they uses 2 or more more than 2 its donor sides to simultaneously to catch only one metal, to bind with a single metal. Okay, it is called a chelate ligand. Okay, so EDTA is one of the example of it. Let's proceed. Okay, specify the oxidation number. Let's do one by one. For the first, number 1 we will do first. Okay, so for cobalt we will take as X, for water it is 0, for cyanide it is -1. For ethylene diamine again it is 0 equals to +2. So X value is becoming +3. Okay, number 2 PtCl4 2 minus. Okay, so here you can see X plus for the chlorine -1. So -1 into 4 equals to -2. Hence I am getting X equals to +2. Right. Next, number 3. X for chromium, ammonia it's going to be 0 plus 3 into -1 for chlorine equals to 0, right? So X is going to be +3. Next, 4 for cobalt, let's take X plus for bromine -1 into 2, ethylene diamine 0 equals to +1. So X is going to be +3. That's it. Okay, I guess it's clear to you. Let's proceed. Okay, using the IUPAC norms, write the formulas for the following. One by one we will write. First one, you can see tetrahydroxidozincate 2. Okay, so Zn with OH whole 4. So zinc oxidation state must be +2, right? So here I will be having 2 minus, right? Next, hexaamine cobalt 3 sulfate. Okay, so cobalt with hexaamine means 6 ammonia. Okay, and sulfate, 3 sulfate, SO4 3. Okay, by default oxidation number will come as 3. Okay, next let's proceed. Wait, this sulfate will go outside. Okay, let's proceed with the third one, that is potassium tetrachloridopalladate 2. Okay, so potassium is cation here, so K2, tetrachloridopalladate, so PD with 4Cl. Okay, that's it. Next, fourth one, potassium trioxalatochromate 3. Potassium chromate 3 means oxidation state must be 3, so K3 Cr trioxalato C2O4 whole thrice. Okay, now chromium also oxidation state 3. 5, diamine dichloridoplatinum 2. Okay, so diamine dichlorinum platinum. Okay, platinum, then diamine dichloride. Okay, I guess this is clear to you. These are the from the IUPAC norms, these are the formulas. Let's proceed further. Using the IUPAC norms, write the systematic names. So just opposite we have to do, we have to write the IUPAC name. CONH3 whole 6 Cl3. Okay, so this is going to be hexaamine cobalt, no space should be there, cobalt, here oxidation state will come 3, then chloride, right? Next one, CONH3 whole 4 ClNO2 then Cl. Okay, so amine we will start with because alphabetically it comes first. How many amine? Tetraamine. So tetraamine, then chlorido, then nitrito. So nitrito is an ambidentate ligand, it is binding from the nitrate end, nitrogen end. So you have to write nitrito N, then you have to finish with cobalt. Here oxidation state will come as 2, 3. Here oxidation state will come as 3. Okay, then you have to end with the anionic part, that is chloride. Okay, let's proceed with the third one. Okay, hexaamine nickel. Hexaamine nickel. Okay, here oxidation state will come 2, then chloride. That's it. Okay, I guess this is clear to you. Let's proceed further. Explain the geometrical isomerism in CN4 with examples. Okay, so here you can see whenever you are having MX2 L2 type of thing, you can have cis and trans isomer. Okay, they will be opposite to each other. Okay, and other square planar like M, A, B, XL, all the 4 ligands are different. For those case also 3 different isomer you will get, 2 cis and 1 trans. Okay, let's proceed further. Why geometrical isomerism is not possible in tetrahedral complex? Because it do not show because of the relative position in the of the unidentate ligands. Okay, they are like the way it attached with the metal in a spatial, in a 3D geometry, it will not show any kind of geometrical arrangement. Okay, I guess it's okay. Let's proceed. What do you mean by optical isomerism? Optical isomerism means they will have the mirror image. Okay, they cannot be superimposable, non-superimposable mirror image. Okay, these are called enantiomers. Okay, so next, they are also called as the chiral compound. Okay, and you can tell that the 2 forms are called dextro and levo. Okay, and they rotate, they can rotate the plane of polarized light in the polarimeter. Okay, if it rotates the right to the right, then you can call it dextro. If it rotates the light, plane of polarized light to the left, then you can call it levo. That's it. Next, let's proceed with the next question. Draw the optical isomers of this. Okay, let's draw it. So platinum with 2 chlorine and ethylene diamine, right? Okay, so you can draw it in this way. Optical isomers only we have to draw. So 2 chlorine I am placing on the same plane. Cis we will draw. Okay, this can be your 1 ethylene diamine and this can be your 1 ethylene diamine. Okay, now place one mirror. Okay, and draw the mirror image. Platinum, here Cl, here Cl, here 1 ethylene diamine and here 1 ethylene diamine. If it is your dextro, then it is your levo. Okay, this is how you should draw it. Next, okay, cobalt with 3 ethylene diamine. So let's draw it. So cobalt, so we can place 1 ethylene diamine like that, 1 like this on the plane, 1 like this. Now you can draw the mirror image of it. Okay, CO, here I can place 1 here, I can place 1 here, and I can place on the plane itself. Okay, so here also you can get 1 D, another 1 L. Okay, I guess these are clear to you. Next, out of this following 2 coordination entities, which is chiral? Okay, so for this particular case we have to check for the cis one. Cis is optically active one. So if I just draw the structure for you, you can see for cis only I will draw chromium, 2 chlorine on the plane, oxalate we can draw like this because these are bidentate. Now you can draw the mirror image. Chromium, here chlorine, and here oxalate like this. Okay, 1 D, another one is L, like that you can represent. Okay, so here if you just draw the trans, if you just for your reference I am telling, this is your cis isomer. Okay, this is your cis. In case if you want to draw the trans, you will see the plane of symmetry pass through it. Let me just show you once. Here let's say in the plane oxalate is there, and above I am having chlorine. So here you can see this is the plane of symmetry. This is the plane of symmetry. Okay, as a result of this, this is your trans, right? Trans is not optically active. Okay, this is not optically active. I guess this is clear to you. Let's proceed further. Explain linkage isomerism. So linkage isomerism arises in a coordination compound containing ambidentate ligand. Here you can see for this particular compound, nitrogen end is binding. If I want to write the isomer, then it will be something like this, ONOCl2, right? Let's proceed. Ionization isomerism. So it happens because of the presence of the counter ion. Once it is placed in the inside the coordination entity, another time it is outside. You can see the example, once sulfate is inside the coordination entity and here it is outside, bromine is inside, like that. Let's proceed. Solvation, it's a number of water that is present inside the coordination entity and outside. Here you can see only 6, I mean all the 6 H2O inside, this is violet, but here for this case 1 H2O outside, it is grey green. Okay, let's proceed. Explain the coordination isomerism. Coordination isomerism, this arises because of the interchange of the ligand between the cationic and anionic entities. You can see here the ligands, here NH3, here CN. If I just alter them, CN and NH3, then I will get the coordination isomerism. Let's proceed. Explain VBT. Here you can see this is the entire VBT explanation. There is a hybridization of N-1D, NS, NP. This orbital hybridization takes place, overlap of this orbital takes place and their energy becomes equivalent. Okay, so they can form octahedral compounds, they can form tetrahedral compounds. Okay, so that's it. Okay, so this is all about the VBT. Let's proceed. Here we have to explain the hybridization, magnetic property and geometry. So cobalt 3+ here, cobalt 3+ is basically 3d6 geometry, right? So if I just draw the 3d6 one, I am having also 4s, I am having 4p as well. This is my 3d, this is my 4s, this is my 4p. So it will be looking something like 1, 2, 3, 4, 5, 6, like that. Okay, so now what I have to do, once the ammonia will approach near to the cobalt center, then what will happen? Force pairing will take place against the Hund's rule. Why? Because ammonia is a strong field ligand. So if force pair takes place, this will be paired up here, this will go there. Okay, so let's just do it. 1, 2, 3, 4, 5, 6. Okay, and these orbitals will be there. So now hybridization will take place along with this 1s and 3p. So D2 sp3, this is the hybridization. And now here in this hybrid orbital, once it is made, it will be looking something like this. Wait, 1, 2, 1s, 3p. Okay, so all the ammonia will donate their lone pair here. Okay, so this is how. So overall geometry is coming as D2 sp3. Now if you just ask about the magnetic property, no unpaired electron, right? Here all the electrons are paired up, so I can say it is a diamagnetic compound. Okay, diamagnetic in nature. I guess it is clear to you. Let's proceed. Okay, geometry. Geometry also, for this case I will be having octahedral geometry. One more information I want to share. Octahedral geometry, strong field ligand, inner d orbital taking part in the hybridization. You can also call it as inner orbital complex. Okay, let's proceed further. Give 3 limitations of valence bond theory. So it involves a number of assumptions. It does not give the quantitative interpretation about the magnetic data. Like it does not explain the color, why the color comes in coordination compound. Then this type of thing you can give actually. It does not distinguish between weak field and strong field ligand. Any 3 you can give out of it. Next, explain CFT, crystal field theory. So basically it's an electrostatic model which considers the metal ligand bond is ionic. means electrostatic interaction we have to consider. Metal is a point positive charge, ligand is a point negative charge. So at first what happens, the metal and ligand, they comes close to each other because of the Coulombic interaction only. Then what happens, ligand is having its own electron sphere, and metal is basically having its own d orbital electron. So when they come close to each other, splitting takes place, inter-electronic repulsion takes place. As a result of this, d orbital gets splitted. Okay, so 3 orbital, they gets minimum repulsion, their energy becomes below, and 2 orbitals, their energy becomes high, that is Eg, and the orbitals, they are getting lower energy, they are togetherly called as T2G. Okay, so T2G are basically dxy, yz, dzx, and Eg are basically dx square, y square, dz square. That's it. Okay, so I guess it's okay, it's clear. So definitely, if you are having a very strong field ligand like Cn minus, CO, okay, this type of ligand if you are having, then the splitting energy will be more than that of the pairing energy. Then during the electronic configuration, while you are just going to fill up the electron, then pairing will take place at first rather than that of going to the Eg level. But if you are using a very weak field ligand like F minus, Cl minus, then pairing energy will be more than that of the splitting energy. In those cases, pairing will take place in T2G, then it will jump to Eg. That's it. Let's proceed. This is the figure for the octahedral splitting, you can see. Let's proceed. It is a tetrahedral, just T2G and Eg. Don't call it Eg or T2G. G term will not be used for the tetrahedral. Only E and T2. Their position will be changed as well. Okay, E will come below, T2 will go up. Okay, let's proceed. What is spectrochemical series? Explain the difference between weak field and strong field ligand. A spectrochemical series is basically the arrangement of the ligands in the increasing order of their crystal field splitting energy. Okay, and next question kya tha? Difference between them. Okay, the ligand that is present in the right hand side, they are strong field ligand, and if they are in the left hand side, they are basically weak field ligand. And definitely strong field ligand, they causes higher splitting in d orbitals, and weak field ligand, they causes lower splitting. Okay, for them pairing energy becomes more. Let's proceed. What is a crystal field splitting energy? How does the magnitude of del O decide the actual configuration of d orbitals in coordination entity? So basically what happens when ligand approaches to the metal center, then d orbital splits in two different set. One is T2G, another one is Eg, right? The energy gap in between these two orbital is basically called as crystal field splitting energy. Okay, next, how does the del O decide? Okay, so definitely it depends basically upon the ligand that you are using. If you are using a strong field ligand, then splitting energy will be more than that of the pairing energy, right? Then pairing will take place in T2G, then the electron will go to the Eg, right? Next, if you are using weak field ligand, then splitting energy will be lesser than that of the pairing energy will be more. So the electron will be go to the Eg, then it will come to the pairing. That's it. Let's proceed. This is what it is written here as well. Let's proceed. Okay, CrNH3 3 plus is paramagnetic, while NiCN 2 is diamagnetic. The reason again is the field of the ligand. Cn is a very strong field ligand. As a result of this, it will cause force pairing in the d orbitals of the nickel. As a result of this, you will get no unpaired electron over there. Hence, it will come up to be a diamagnetic. Whereas, if you look for the ammonia, in that case, it will not force pair the electron, right? As a result of this, unpaired electron will be there, you will get paramagnetic character. Okay, I guess it's clear to you. Okay, again the same type of question. This is strong field ligand, this is weak field ligand. Strong field ligand will force pair, right? And you will not get any unpaired electron, hence diamagnetic. Cl, weak field ligand, unpaired electron will be there, no force pairing, right? Hence paramagnetic. Okay, let's proceed. FeH2O whole 6 3 plus is strongly paramagnetic, whereas the same reason you can see because of the unpaired electron. Next, okay, a solution of NiH2 whole 6 2 plus is green, but a solution of NiCN 2 minus is colorless. So the reason is the weak the field of ligand. H2 is a weak field ligand, right? So as a result of this, unpaired electron is present, and unpaired electron means it will undergo D to D transition, right? And hence you will see the color. But whenever it comes to the matter of CN, for this case what happens? No unpaired electron is present because it will force pair the electrons, hence there is no D to D transition, hence no color. Okay, proceed. Okay, FeCN6 4 minus and FeH2O6 are different in color in dilute solution. So the reason is basically the same. The color it definitely depends upon the crystal field energy, right? For FeCN6 it's a very strong field ligand, right? So as a result of this, higher CFSE value we can expect, right? But for H2O, comparatively lower CFSE value, D to D transition will be different, right? For strong field ligand, CFSE value is more, hence D to D transition will be more, hence you can see color, different color, right? But for H2O, ligand field is low, CFSE value is low, hence D to D transition, it will also differ, right? So different color you will observe. Let's proceed. Explain the violet color of the complex, this on the basis of crystal field theory. Okay, so definitely any crystal, any complex compound, they exhibit color because of the D to D transition. For this particular case, TiH2O whole 6, like here what happens, light, in case of this, when light corresponding to the energy of blue-green region is absorbed by the complex, it will excite the electron from T2G level to EG level. Okay, so if blue light is absorbed, then its complementary color will be released. So complementary color is basically the violet color. That's why violet color you can see from outside. Okay, let's proceed. Anhydrous CuSO4 is white, but CuSO4 5H2 is blue in color. Again, due to the heating, water molecule evaporates from the crystal of CuSO4 and it becomes anhydrous. Okay, so there is no splitting in that particular case and no DD transition, but that's the reason your anhydrous compound is colorless. Let's proceed. What will be the correct order of the wavelengths of absorption in the visible region? Okay, this is also depends upon the ligand field. NO3 minus will come first, then NH3, then H2. So for this case also, the correct order of the wavelength of absorption, H2 will come first, then NH3, then NO2. Okay, let's proceed. Discuss the nature of bonding in metal carbonyls. So here comes synergic type of bonding. So synergic type of bonding, what happens basically, metal carbon bond, usually a sigma bond that takes place in between S and P orbital. Okay, S and P both characters are there. Okay, so what happens basically, carbon at first gives the electron cloud to the metal center and it forms the sigma bond. Further what happens, metal gives the electron cloud back to the carbonyl and it creates some pi character as well. Okay, so it has both sigma and pi character. Okay, so carbonyl accepts the electron cloud in its anti-bonding pi star. Okay, so as a result of this, both sigma and pi character, some back bonding character you will get out of it, that is called synergic bonding. Okay, let's proceed. Aqueous copper sulfate solution gives a green precipitate with aqueous potassium fluoride and a bright green solution with aqueous potassium chloride. Explain. Okay, so basically if you just check aqueous copper sulfate, here in the coordination sphere itself the water molecule exists, outside SO4. Okay, now it is blue in color due to the presence of these ions, right? Next you can see whenever Kf is added, then it will form CuF4 2 minus. okay, and whenever KCl is added, it is from CuCl for 2 minus. Okay, so both case it is weak field ligand. Okay, now water is replaced by F and Cl, right? That's the reason you will get different color. One is green, another one is bright green. Okay, for fluorine it is a little bit more than Cl, the field of the ligand. Then that's the reason, as water is replaced by comparatively weak field ligand, that's the reason there will be the change in color. A green precipitate for the fluorine compound and bright green for the chlorine. Okay, let's proceed. What is a coordination entity formed when excess aqueous KCN is added to an aqueous solution of copper sulfate? Why is it that no precipitate of copper sulfide is obtained when H2S gases pass through it? So basically, whenever this copper aqueous solution of copper sulfate, it exists in this form, CuH2O whole for 2 plus. Excess KCN, if you add Cn minus, it forms this complex. Okay, CuCN for 2 minus, water is replaced with Cn. Okay, as a result of this, this particular compound is very stable. Okay, this particular compound is very stable because Cn minus is very strong field ligand. Okay, so this is the coordination entity that is formed out of it. This is the coordination entity. Okay, next part is why there is no precipitation. If you pass H2S gas, then copper sulfide precipitation will not be obtained because copper is a part of the coordination sphere, and coordination sphere, it will not dissociate, right? Hence copper sulfide you will not get. Let's proceed. Okay, so that's it. So that's all about the entire coordination chemistry and D and F block that also we finished here. Yes, these many questions will be more than enough for your upcoming PU2 examination. So make sure, if you have not subscribed this channel, please subscribe, click the like button and share with your other friends so that they can also get the benefits of this video. Thank you so much for watching. Hello my beautiful PU2 aspirants, so welcome back to a new session where I am going to discuss all the probable question on the organic chemistry. So here a little bit MCQ, 2-3 marker, all type of questions we will discuss that you may face in your upcoming organic examination. So a lot of things needs to be discussed. Yes, without further delay, let's get started. So first we will start with the chapter haloalkanes and haloadenes. So here this is the marks distribution. You can see very small answer type you can get 2 out of it, small answer type you can expect 1, a large answer type 1. Explain Swartz reaction with an example. So here we are starting the 2 marker question. So Swartz reaction, I guess you know, just you have to prepare fluoride, right? Alkyl fluoride type of compound from alkyl chloride or bromide. You can use any kind of metal fluoride as a reagent, silver fluoride, mercurous fluoride, this type of thing. Okay, this is the reaction you can see. Let's proceed. Finkelstein reaction, here you can see whenever alkyl chloride or bromide, you are treating it with sodium iodide in presence of acetone, you will get iodide, alkyl iodide type of compound. That is Finkelstein. Okay, let's proceed for the next question. How do you prepare alkyl halide from alcohols? Okay, so from alcohols, if you start this ROH and if you just treat this with SOCl2, you will end up with RCl type of compound, and along with that SO2 gas is prepared. So as the byproducts are gases, then you don't have to be worried that there will be contamination with other products. So you will get the alkyl halide in a larger content. So let's proceed further. A hydrocarbon do not react with Cl2 in dark but react in sunlight to give monochloro compound, that is C5H9Cl. Identify the hydrocarbon. Okay, so general formula is something CnH2n, and if it is CnH2n, then there are 2 possibilities. It can be either alkene or it can be cyclic structure. Now it does not react with it does not react in dark condition, right? It means that it's a cyclic structure. It cannot be a double bond, right? Now monochloro compound, it represents that all hydrogens are equivalent here. So the compound must be something like this. Okay, let's proceed further. Give the preparation of aryl halides by Sandmeyer's reaction. Okay, so preparation of aryl halides. So if you just start simply with aniline on being treated with HNO2, means NaNO2 plus HCl at 0 to 5 degrees Celsius, it will prepare benzene diazonium chloride, right? That is N2 plus Cl minus. So N2 plus Cl minus, if you give now Cu2 Cl2 in presence of HCl, the entire N2Cl group will go, and here your Cl will come, and here you can see nitrogen gas will be eliminated. So this particular step is called Sandmeyer's reaction. Okay, so let's proceed. In haloarenes, para isomers have higher melting point as compared to that of the ortho and meta, just because of the symmetry. Para compounds are more symmetrical than that of the ortho and meta. That's the reason they have higher melting point. Okay, let's proceed. Arrange in increasing order of boiling point. First is bromomethane, bromoform, chloromethane, dibromomethane. Okay, so here you can see definitely bromine is molecular weight, electronegativity, not electronegativity but molecular weight, with respect to that it is heavier than that of chlorine, right? So expected that boiling point will be more for bromine as well, right? So now here bromoform means I am having 3 bromine in it, right? After that dibromine, right? Dibromomethane, right? So first 3 bromine compound, after that 2 bromine compound, then bromomethane, right? Single bromine compound, then chlorine compound. So you can see this is the order: bromoform, dibromomethane, bromomethane, chloromethane, like that. Okay, next you can see 1 chloropropane isopropyl chloride and 1 chlorobutane. So definitely 1 chlorobutane will go first, okay, because of the atomic weight. First of all, yes, chlorine is there everywhere, but the thing is 1 chlorobutane, if you see the structure, it has more surface area, right? Next, if you see 1 chloropropane, so 1 chloropropane, why? Because the number of carbon atom reduced here, okay. And isochloride chloride, if you see, it has a little bit branch over here, so surface area decreases, so it will come last. Okay, let's proceed. Write the steps involved in SN1 mechanism for the conversion of tertiary butyl chloride to tertiary butyl alcohol. So tertiary butyl, here bromide they gave the example. Anyway, you can take it as chloride, it's quite similar. So first step, the carbocation generation. So after generation of carbocation, the OH minus, that is the nucleophile, it will attack on it and you will get your desired alcohol, tertiary butyl alcohol. Okay, so make sure that you are mentioning what is rate determining step. Step 1 is the slowest step, here it is the rate determining step. Okay, let's proceed. Write the steps involved in SN2 mechanism for the conversion of chloromethane to methanol. So here you can see I am having chloromethane, this particular compound, whenever the OH minus will attack here, a penta-coordinated transition state will be generated, then your living group will leave the system and you will get the distorted or tilted structure. Okay, let's proceed. Haloalkanes react with KCN from alkyl cyanide and with AgCN from isocyanide. Okay, so whenever KCN is like mixed in water, okay, it ionized to give you K plus and Cn minus, means ionic bonds are there. But whenever it's mixed with AgCN, no, then in between silver and carbon there exists covalent bond. Okay, and a little bit back bond character, that's the reason Ag and Cn, they doesn't ionize properly. So from the nitrogen end they bind. Okay, from the nitrogen end they are free to donate, right? That's the result, they form the isocyanide type of compound. But for KCN, carbon end it reacts, that's why we get the cyanide. Okay, let's proceed. Electrophilic substitution reaction occurs slowly in haloarenes compared to that of the benzene. So basically what happens, due to the minus I effect, haloarenes have more tendency to withdraw the electron from the benzene ring, right? So as a result of this, the ring gets deactivated, right? So once the ring gets deactivated, then why electrophile will attack over there? But in benzene there is nothing to deactivate the ring, so simply electrophile can come and attack over there, right? Let's proceed. Aryl halides are less reactive towards nucleophilic substitution. Give reason. So first is the resonance effect. Due to the resonance effect, what happens? Carbon and halogen bond, that particular bond has partial double bond like character. So once I am having the partial double bond like character, it's difficult to substitute, right? Why the bond will break, right? Now next is sp2 hybridization of the carbon, right? So due to sp2 hybridization, carbon in CX bond has more S character. Okay, as a result of this, the bond becomes very strong. They hold each other with a very with very strong bond. Okay, I guess it's clear. Let's proceed. Okay, explain Fittig's reaction, Woods-Fittig reaction. Okay, Woods-Fittig reaction, the first one you can see this one. Okay, this is Woods-Fittig reaction. You must have one alkyl halide and one aryl halide. They will give you the alkyl benzene type of thing, right? Now aryl halide, if you take 2 units in presence of sodium and dry ether, they will give you diphenyl type of compound. This is the Fittig reaction. Okay, let's proceed. What are Grignard reagent? Write its general formula. So it's a organomagnesium compound, organomagnesium halide you can say, or bromide you can say. They are called Grignard reagents. So usually we denote it as RMgX. X is the halogen over here. Okay, what are the freons? Name the poisonous gas evolved when Cl2 is oxidized by air. So you can see the chlorofluoro compounds of methane, they are effectively called as freons, and whenever Cl2 will be oxidized, you will get phosgene gas. Okay, so that is poisonous for your health. Let's proceed. Chloroform is stored in closed dark colored bottle. Why? Because it gets slowly oxidized to give you the poisonous gas phosgene. Okay, so this is the formula. You can see chloroform in presence of oxygen, it forms phosgene and HCl. Okay, that's the reason it is placed in the dark colored bottle. Okay, next, complete the following reaction. Okay, so here for the first case, I will proceed with the Markovnikov mechanism. Here I will be having the Br, here CH3, here hydrogen, right? Here I will be having one more hydrogen, right? This is Markovnikov mechanism. Okay, now this particular thing I can start from ethane. Okay, 2 units of ethane I can start with, and this particular thing will give you phenol. Okay, now explain Saidzev rule with an example. Saidzev rule states that whenever elimination takes place, such as dehydrohalogenation or that type of thing, then major alkene product will be that one which will be more substituted. Okay, so one example you can see, if you this is 2-bromobutane, right? If you are having 2-bromobutane type of thing, if you are having 2-bromobutane, then after the elimination you can get 2 type of product. One is this, one is this. Means here I am having hydrogen, right? Here I am having hydrogen, this will jump here, bromine will be released. So here double bond, and another one is here double bond. Okay, but this one will be formed as a major one. Why? Because this particular alkene is more substituted. You can see number of alpha hydrogens are more here, but here it is less substituted, hence this is the minor product. So this is the Saidzev rule. Let's proceed further. Next, write any 3 differences between SN1 and SN2 mechanism. Identify A and B. Okay, this is the SN1, SN2 mechanism. Any 3 you can take. Okay, I'm not explaining again like first order, that is a second order. That type of thing you can just take any 3 and you can just note it down. Okay, identify A and B in the given reaction. Okay, just let me do it here. So I'm having aniline. So aniline in presence of NaNO2 HCl. NaNO2 plus HCl, it will form HNO2, 0 to 5 degrees Celsius, it forms benzene diazonium chloride, it forms N2 plus, okay, Cl minus, okay, benzene diazonium chloride, that is my A. Right now, if you proceed with the B, you need Br, right? So I can give Cu2Br2 in presence of HBr, that is your Sandmeyer's reaction, okay, and you will end up with Br here. Okay, I guess it's clear. Okay, write the mechanism involved in the conversion of 2-bromo to methyl propane. Okay, so this particular thing we did already. 2-bromo to methyl propane. Okay, so here you can see 1, 2, 3, if I just name it, 2-bromo, 2-methyl propane. So definitely this will undergo SN1 type of mechanism. We already did it here. Let me just show you again. This thing, okay, the same mechanism will be followed over there to get the alcohol. Okay, so yeah, let's proceed. Next, what are enantiomers? Name one physical property which differs the enantiomers. So enantiomers, they are basically the pair of chiral molecules that are non-superimposable mirror image of each other. Okay, so they have definitely their own physical identities, own physical properties like melting point, boiling point, solubility, okay, like that, and they differ in optical activity. One, if you are having dextro, then it will rotate the plane of polarized light in the right side, right hand, and if you are having levo, then it will rotate the plane of polarized light to the left side, okay, to the anti-clockwise direction. One is clockwise direction and one is anti-clockwise direction. That's it. Let's proceed. Write the equation for the steps involved in SN1 mechanism. That already we did. Hydrolysis of 2-bromo, same thing. Hydrolysis means you have to add OH over there. Same thing only. Name the product formed for the reaction of isopropyl iodide on alcoholic KOH. Okay, so let me show you this isopropyl iodide. This is your isopropyl iodide, right? So if I just write it in this way, I can write it in this way, right? So in presence of alcoholic KOH, right? Alcoholic KOH, it will undergo beta elimination or dehydrohalogenation. So this will jump here, this will be removed. So you will get this CH double bond, CH single bond. Okay, this is CH3. CH2 double bond CH, CH3. You will end up with this thing, propene. Okay, I guess it's clear to you. Let's proceed. What is the condition to be satisfied for a compound to be chiral? So the condition, I guess you know, there must not be any plane of symmetry, right? So in that case the compound will be chiral. Next, what is a racemic mixture? This is a equimolar dextrorotatory and levorotatory isomers. If you are having, then it is called racemic mixture. Let's proceed. Okay, so these are the important topics that already covered over here: the definition of retention, inversion, stereocenter, enantiomers, racemic mixture that you can proceed. Some name reactions are very important, like Schwartz reaction, Finkelstein, Dawes process. Dawes process means whenever I am adding SOCl2, that's method. Okay, SOCl2 in alcohol to give you aryl halide, alkyl halide. Friedel-Crafts reaction, Woods fatigue, Sandmeyer's reaction, and mechanism SN1 and SN2. If you are done with this, then yes, your haloalkanes, haloarenes chapters are sorted. So yes, let's proceed for the next one, that is alcohols, phenols and ethers. Okay, this is the marks distribution. You can see very small answer type you can get 3, small answer type you can get 1, and large answer type you can get 1. Proceed further. So this is the preparation of alcohol. Overall in a single slide it is represented. Okay, so on basis of this only the question can be solved. Proceed. Write the product. Okay, for this case if you are doing B2H6, then it will undergo anti-Markovnikov mechanism, CH3 CH2 CH2OH. Okay, this is anti-Markovnikov. Anti-Markovnikov, and here I will get Markovnikov, that is CH3 CH, here OH, here CH3. Okay, this is Markovnikov. That's it. Let's proceed. What is hydroboration oxidation reaction? Give an example. Here you can see this is a hydroboration oxidation if you are having alkene unit on being treated with B2H6 or diboron. Okay, so diboron followed by hydrogen peroxide, okay, in alkaline medium gives you the alcohol, that is the hydroboration oxidation reaction. So this particular case boron atom, it gets attached with the sp2 carbon, okay, and further it continues for the alkylation until it is having the all hydrogen replaced by the alkyl group. Then if you treat it with H2O2 in OH minus, it will be converted to the alcohol. That's it. Let's proceed. Give 2 methods to prepare alcohol from carbonyl compound. So what you can do is you can do the hydrogenation by in the presence of catalyst like platinum, palladium or nickel, or you can reduce the carbonyl group with the lithium aluminum hydride to give you the alcohol. Okay, so how will you prepare 1 degree alcohol from carboxylic acid? Same thing, you can treat this with lithium aluminum hydride to give you the alcohol. Proceed. How to prepare alcohols commercially from the carboxylic acid? So we can do esterification reaction. Here you can see you can treat this with the alcohol group. Okay, ester you will get once you get the ester, then it will undergo hydrogenation. Okay, reduction, you do the reduction or hydrogenation in presence of some sort of catalyst, it will give you the alcohol. Okay, let's proceed. How to prepare 1 degree, 2 degree and 3 degree alcohols from Grignard reagent. So 1 degree alcohol you can treat Grignard reagent with HCHO. Okay, so let me just show you the equation one by one. This is your HCHO. If I give Grignard reagent, let's say RMgBr, so this will attack over here, this will be opened up, so you will get something like, and if I give followed by H3O plus as well, if I give H3O plus as well, this here OH, here you will get R group. So you can say this is in 1 degree. Now 2 degree alcohol you can get any kind of from any kind of aldehyde. Let's say I am taking CH3CHO. Okay, now let's say I am adding CH3Mgb here. Okay, so CH3 will attack here, this will open up. If I treat this with H3O plus further, then I will get something like this. CH3, here C, here I will get OH and here CH3. Right, so this is your 2 degree. Now for 3 degree, you have to treat the Grignard reagent with a ketone. So CH3, C double bond O, CH3, I am having acetone. Now let's treat it with CH3Mgb here. Okay, this CH3 will attack here, this will open up, followed by H3O plus if you give, then you will end up with this thing. Here you will get OH. Okay, I guess this is clear to you. Okay, let's proceed further. Boiling points of alcohols are higher than other classes of organic compounds like hydrocarbons, ethers, haloalkanes of comparable molecular mass. Give reason. The reason is hydrogen bond. Okay, hydrogen bond, intermolecular hydrogen bond makes the two alcohol unit to be attached together. So to break them you need more energy, right? Next, alcohols are soluble in water. Again, alcohol can form the hydrogen bond with the water. That's why it is soluble. So I guess it's clear. Let's proceed. So this is all about the cleavage of OH bond related reaction. Okay, so involving this we can solve the rest of the question. First question, what is the effect of electron donating substituent on the acidity of the alcohol? So if you are having electron donating substituent, then if electron donates, let's say I am having CH2, here OH, here I am having some electron donating group. So if electron is donated here, so oxygen will be more electronegative, right? The electronegativity on oxygen will be more. So oxygen hydrogen bond will not be broken quickly. Oxygen hydrogen bond will not be broken quickly, hence acidity will decrease. Acidity will decrease, right? So okay, next, alcohols are weaker acid than that of the water. The reason is same, because if you just see water, there is this is the electronic effect is the reason. There is no alkyl group present over there, right? But if you see ROH, this particular thing is having plus I effect, electron donating effect, so it will donate the electron towards the oxygen. Okay, so it will increase the electron density. Electron density will be increased on oxygen, hence acidity decreases. Okay, acidity decreases. Here also the same reason. Okay, I guess it's clear. Let's proceed. Here it's given the explanation. Let's proceed. What is esterification reaction? Give an example. So esterification reaction is basically reaction between the carboxylic acid and one alcohol in presence of catalytic amount of H plus. Okay, so this is called esterification reaction. Okay, what happens when ethanoic acid reacts with the methanol in presence of H2SO4? Definitely esterification takes place. So ethanoic acid, let me just do this thing for you. CH3 COOH plus, let's say, methanol CH3OH. CH3OH in presence of H plus, catalytic amount of H plus if you give, it will form the ester. You will end up with this thing. Okay, so I guess it's clear. Let's proceed further. So this is the reaction of entire alcoholic unit, entire OH unit. Okay, so let's proceed. What is Lucas reagent? How would you distinguish between 1 degree, 2 degree and 3 degree alcohol by Lucas reagent? It's a mixture of ZnCl2 and concentrated H2SO4. Next, how would you distinguish? Tertiary alcohol means 3 degree alcohol. They produce instant turbidity, because it proceeds through SN1 mechanism. It proceeds through SN1 mechanism. So once I am proceeding this thing with SN1, so tertiary alcohol will form stable carbocation, right? So it gives instant turbidity. Secondary alcohol within 3 to 5 it gives this turbidity, and primary alcohol it doesn't react. Okay, means the reaction is very slow in the room temperature. Okay, so if you heat this, definitely the reaction will take place. So if you get instant turbidity, you can tell that it's a 3 degree. If you have to wait for 3 to 5 minutes, it's 2 degree. If in the room temperature the reaction does not at all is occurring, then you can tell it's a 1 degree. Okay, let's proceed. So this is the oxidation reaction with CrO3, PCC and Cu. Okay, let's proceed with the first question. What happens when the vapors of 1 degree, 2 degree and 3 degree alcohol passed over heated carbon at 573 Kelvin? So here comes the answer. You can see this is the 1 degree, this is 2 degree and this is 3 degree. Okay, 1 degree will form the aldehyde, 2 degree will form the ketone, 3 degree will form the alkene. Okay, let's proceed. Okay, what is rectified spirit, what is absolute alcohol, and what is denaturation? So rectified spirit, you know the formula, 95.5% pure ETOH, ethanol, right? And what is absolute alcohol? Absolute alcohol is 100% pure ethanol. Next, denaturation of alcohol is commercially alcohol, they mix something CuSO4 and pyridine for bad smelling, okay, to make it unfit for the drinking, okay. So this phenomenon is called denaturation of the alcohol, okay. Let's proceed. Describe the manufacture of ethanol from fermentation of sugar, okay. So here what we do, whenever you are having sugar, okay, sugar on being hydrolyzed, it will give you the glucose and fructose, okay. Now definitely in case in commercially you have to use some enzyme over here, so you need invertase, okay. Later on that glucose and fructose that you got, they will again undergo fermentation in presence of another enzyme that is called zymase, that will give you the alcohol, that is ethanol, okay. I guess it's clear. Let's proceed. So this is the preparation of phenol, these are the reactions. Proceed. Okay, how would you prepare phenol from benzene via sulfonation? So here you can see benzene can be treated with the oleum at first to get the sulfonic acid, benzene sulfonic acid. So in sulfonic acid, treat this thing with NaOH and then H plus, you will get the OH. This is the reaction. Next, how would you prepare the phenol from diazonium salt? From the diazonium salt, you direct to hydrolysis, directly you treat this with water, you will get the phenol. How would you prepare phenol from cumin? It's a very important thing actually, okay. This is the diazonium thing. Next, this is the next thing, that is how would you prepare the phenol from cumin. So cumin at first oxidized in presence of oxygen to get the cumin hydroperoxide type of compound, that will further on being hydrolyzed you will get OH, okay, I mean phenol and acetone, okay. I guess this is clear to you. Cumin to phenol synthesis is very important. Next, alcohols are less acidic than that of the phenol. The reason is in alcohol alkoxide ions are formed, and in phenol phenoxide ions are formed. So in phenoxide what happens? The benzene ring, they get some extra stability due to the resonance. That's the reason these alcohols are less acidic than that of the phenol, because phenoxide ion is more stable, right? Conjugate base is very stable, right? Next, give a chemical reaction to show phenols are more acidic than that of that. You can just treat this thing with NaOH. Phenols can react with NaOH, but alcohol, normal alcohol, they cannot react with NaOH, okay. Next, what is the effect of following group on acidity of phenol? Okay, so first case, this is an electron donating group. So electron donating group, if it is attached, then acidity of phenol will decrease. Acidity will decrease because it increases the electron cloud density on the oxygen atom, right? And for this case, this is an electron withdrawing group. Electron withdrawing group. So it increases the electron cloud density on oxygen, and hence it decreases the electron cloud density on oxygen, and hence acidity increases, okay. Let's proceed. Among the orthonitrophenol and phenol, which one is having higher pKa value? So orthonitrophenol, if you just draw this structure, you can see So this is the structure of orthonitrophenol, right? So you can see in presence of the NO2 group in the ortho position, it can form nice intramolecular hydrogen bonding, right? Intramolecular hydrogen bonding. As a result of this, a 6-membered stable ring is formed over here. So why the oxygen will release the hydrogen, right? So that's the reason acidity here decreases, and acidity and pK, they are inversely proportional, right? So acidity decreases, hence pKa increases. Now if you just look for the phenolic OH is ready to be released. It can be released without any influence because no other groups are present. So pKa value should be more than that of this. Okay, pKa value is decreased here. So highest pKa value you will get in orthonitrophenol. Okay, and this is for the phenol. Okay, this is more, this is less. Next, this is the cleavage of OH bond related reaction. Let's proceed. How would you prepare aspirin from the salicylic acid? So you have to undergo acetylation reaction. So acetic anhydride if you give in presence of H2SO4, it will form the aspirin, and the name, IUPAC name of aspirin is 2-acetoxybenzoic acid. You can see this is the reaction, this is your salicylic acid. If you just treat this with acetic anhydride, it will prepare the aspirin. Along with that you will get ethanoic acid. Okay, let's proceed. There is a reaction of phenols. You can see whenever it is treated with bromine, HNO3, all the reactions are covered here. Let's proceed with the questions. Electrophilic substitution reaction of phenol occurs at ortho and para position. Why? Because in the ortho and para position, if you see, because of the resonance, the electron cloud density becomes more. See, negative sign comes in the ortho and in the para because of the resonance. So if any electrophile that is positively charged, if it wants to enter into the ring, which position it will choose where the electron density is more? So it will choose the ortho or the para position. I guess it's clear. Let's proceed. Among ortho and para nitrophenol, which has higher boiling point? So definitely para nitrophenol is having higher boiling point because it will form intermolecular hydrogen bonding with another molecule of para nitrophenol. But in case of ortho nitrophenol, it is having intramolecular hydrogen bonding and it is steam volatile. Okay, so using the steam distillation method, you can separate if you are having the mixture of ortho and para substituent. Let's proceed. Okay, you can see orthonitrophenol is steam volatile, but paranitrophenol it's not. Why? Just because of intramolecular hydrogen bonding that I just explained. And how would you separate? Using the steam distillation method. Proceed. Name the products formed when phenol is treated with bromine water. So if phenol is treated with bromine water, you will get both ortho para substituted bromine. This thing. Okay, now if you are having the bromine only in CS2, then mono substituted you will get either in ortho or in para. Like this. I guess this is clear to you. Let's proceed. Okay, this is some more reactions. Okay, explain Kolb's reaction and how do you convert phenol to salicylic acid. I guess I don't have to tell this, it's a direct name reaction, and directly only they ask this question. If phenol, if you treat it with NaOH, it will first it will get converted to ONA, then treat this with carbon dioxide, it will give you salicylic acid. That's it. What's Riemann-Tiemann reaction? So what you have to do, chloroform you have to treat in the presence of aqueous NaOH. Okay, then H plus if you give, you will end up with salicylaldehyde. Okay, let's proceed. Name the product formed when phenol is treated with chloroform in presence of NaOH. Just now we did this reaction. Okay, we will end up with salicylaldehyde. Next, CCl4 in presence of NaOH followed by hydrolysis. So that case also we will get salicylic acid. Okay, let's proceed. What happens when phenol is treated with zinc dust? Phenol is treated with zinc dust, you will get benzene. Okay, so next, explain the oxidation of phenols. If you oxidize the phenol in presence of Na2Cr2O7 like or chromic acid, then you will get benzoquinone type of compound. Okay, Proceed further, explain Williamson ether synthesis with an example. So if you take any alkyl halide and alkoxide ion in alcoholic medium, then it will undergo SN2 type of reaction. So this O minus will attack over this carbon, the chlorine will leave the system and you will end up with the ether. That is your Williamson ether synthesis. Okay, let's proceed with the question. Which of the following is the best method for the preparation of tertiary butyl ether? Give reason. Okay, for this case, option 2 is going to be the better option, better choice. Why? Because if you want to form the ether, then definitely it must proceed through SN2 mechanism. So if SN2 mechanism, if you start with this, then the backside will be hindered, right? So from where the ethoxide unit will attack, the backside is hindered, right? So but for this case, if this is your alkoxide, means this, see here Me, if this is your nucleophile, then it can attack on this group nicely. It can attack nicely and Cl will be thrown out. So you will get Me, O, CH2, CH3. Okay, I guess this is clear to you. Always remember that Williamson ether synthesis will proceed through the, SN2 mechanism. So backside must not be hindered. Okay, proceed. What happens when diethyl ether is heated with limited amount of HI and excess amount of HI? So if diethyl ether is heated with limited amount of HI, will end up with the ethyl iodide and ethanol first. And if you do excess, if you treat this with excess, then that ethanol that was formed, that will be also replaced with iodine. Okay, ethanol in presence of HI, it will give you the ethyl iodide. So overall you will get ethyl iodide whenever excess HI is treated. Okay, let's proceed. Complete the following reaction. Mention whether the reaction is SN1 or SN2. Okay, so here you can see the reaction is basically SN1 mechanism. Okay, so let me just mark the thing for you. If you just treat that with HI, you will get CH3 whole thrice Ci and CH3OH. Okay, and here you can see the reaction of ether with concentrated HI usually proceed through SN2 mechanism. Okay, where what happens, iodide attacks the less statically hindered alkyl group. But in this case, you can see ether has a tertiary alkyl group. See, this tertiary alkyl unit is there, right? So protonation of the oxygen followed by cleavage of the CO bond forms stable carbocation. Let me show you the mechanism. So for this case, what happens? First, OCH3, right? I am having H plus in my medium. So first protonation takes place. This thing is formed first. Okay, after that what happens? After that this group leaves and you will get a stable carbocation. Okay, you will get a stable carbocation. Okay, then what I minus does? I minus attacks on the carbocation and you will get this type of thing. Okay, and definitely if this thing is released, then you will get CH3OH here, right? I guess this is clear to you. Just in order to get a better intermediate, the reaction will proceed through SN1 mechanism. So always focus on the starting material. If SN2 reaction would take place, backside is hindered, from where I minus will attack, right? So that's the reason, to make the reaction susceptible, it will proceed to SN1 mechanism. I guess this is clear. Let's proceed. How HX react with alkyl aryl ethers? Okay, give an example. So it reacts to form phenol and alkyl halide. You can see this is your alkyl aryl ether, this is your arylic unit. this is your arylic unit, this is your alkylic unit, right? If you give HX, then you will get phenol and RX. One example with anisole is also given here. I guess it's clear. Let's proceed. Anisole undergo electrophilic substitution at ortho and para position again, because what happens, OCH3 group is an electron donating group and it increases the electron density in the ortho and para position only. That's the reason electrophilic attack takes place in the ortho and para. Next, explain the nitration of anisole, explain bromination. Okay, this is the nitration mechanism. Here you can see NO2 plus works as a electrophile out of it. So definitely either ortho or in the para position it will attack. So I am showing here the ortho attack. So this double bond will attack over here on the NO2 plus, and you can see here sigma complex will be formed. Then one hydrogen will be taken by water and this carbon hydrogen bond will jump and you will get your para-nitroanisole type of compound. Okay, so majorly you will get basically ortho and para product. Okay, next bromination. Here comes the bromination mechanism. This is ortho, this is para position. Same thing, Br plus is your electrophile here. So Br plus will be attacked by the double bond at first and one sigma complex will be generated. Now to get back the aromaticity, this carbon hydrogen bond will break and the electron will jump here. Okay, as a result of this you can see the aromatic character will come back. So ortho and para. Okay, I guess it is clear. Let's proceed. Explain Friedel-Crafts alkylation and acylation. Okay, in anisole. So this is your alkylation reaction. You can see. So if you treat this with methyl chloride in presence of aluminium chloride, anhydrous aluminium chloride, you will get ortho and para substitute. This is electrophilic substitution. This is your acylation. You have to treat this with acyl chloride, CH3COCl. You will get one ortho, one para. Okay, proceed. Explain the mechanism of dehydration of ethanol to ethene. So first you can see this is the dehydration mechanism. Ethanol, first it will attack on H plus and it will form the protonated alcohol. Okay, so protonated alcohol or ethyloxonium ion you can say. Okay, so once ethyloxonium ion is formed, then carbocation is generated because OH2 plus is very good leaving group. So OH2 plus will leave the system and it will give the carbocation. Now what happens, elimination of one proton will give you back the double bond. So ethene. Clear, I guess. Next you can see, okay, question is identify. So here you will end up with salicylic acid, right? Sorry, COOH. Okay. For this case, what you will get here, alcohol. Already with this type, we did this type of thing. Me, here Me, here Me, here I will get I, right? Let's proceed. Okay, so identify A, B and C. Okay, so in presence of bromine water, A will be both ortho and para will be substituted. So here bromine, here also bromine and here also bromine. Okay, in presence of zinc it will give you the benzene ring itself. Okay, and for this case it will give you the hydrogen gas. Okay, next, how to prepare phenol from aniline. Okay, so what you can do is, wait, you can start from aniline like this. You can treat this with NaNO2 plus HCl. Condition 0 to 5 degree Celsius. It will give you benzene diazonium chloride. N2 plus Cl minus, right? Further, if you just do hydrolysis, give a little bit of water, it will give you back the OH. Okay, I guess this is clear to you. Let's proceed. Explain the mechanism of dehydration of alcohols into ether. So this is the mechanism. Alcohol first you have to protonate, then another alcohol will attack on the protonated alcohol to get OH plus, that type of thing. Then this oxygen hydrogen bond will break down and oxygen will get back its electron. Okay, I guess this is clear to you. How anisole reacts with acetyl chloride, that I already did. Friedel-Crafts acylation, that's the same thing. Okay. Okay, let's proceed with the next question. Explain the mechanism of hydration of alkenes to alcohol. Okay, so let's do first step is definitely protonation of alkene. So let me just take any alkene. So let's take here R group, here H, hydrogen, hydrogen. Okay, so I have H3O plus, right? I have H3O plus, right? So now alkene double bond will attack on the hydrogen. Okay, as a result of this, I will get a carbocation here. So C hydrogen, here one more hydrogen will come here, let's say carbocation. Okay, carbocation will be stabilized here, right? Now next step will be, this is my protonation. Okay, next step is basically nucleophilic attack. Nucleophilic attack. Okay, so who will attack? Water only. So here I am having hydrogen, here R group, cation, here I am having CH3, right? So now water molecule, it has lone pair, it will attack over here. As a result of this, you will end up with something like this. Carbon, here one hydrogen was there, here one R group, here one OH, H here, positive sign, right? And here I am having 3 hydrogen. This is nucleophilic attack. Next is deprotonation. Okay, if you do deprotonation, then what will happen? Just let me write it down again. Here I am having OH2 plus, right? Here R group, here hydrogen, right? Carbon with 3 hydrogen. Okay, now water molecule I am having in my media. So water molecule will take one hydrogen, this bond will jump on oxygen. Okay, and it will end up with one alcohol. Here OH, here hydrogen, and here as it is 3 hydrogen. Okay, so this is the mechanism of hydration of alkenes to alcohol. Okay, so now let's do this reaction. So A is going to be the Markovnikov product, right? So it's going to be CH3, CH, here OH, here CH3. Now further, if you treat this thing with CrO3, it will give you the ketone. Second degree is alcohol, 2 degree alcohol on being oxidized with CrO3 will give you the ketone. I guess this is clear to you. Let's proceed. Okay, this is the mechanism already done here. Okay, let's proceed with the question. An alkene C3H6 react with H2O H plus to give compound Y. Okay, compound Y further undergo reaction with CrO3 H2SO4 to produce Z. Write the IUPAC name of the compound X, Y and Z. Okay, so definitely if you are having C3H6, I can take it like propene. Okay, this on being treated with H2O in H plus, okay, this will give you alcohol. CH3, what type of alcohol? You will get intermediate alcohol because it will follow Markovnikov mechanism, and CH3. Now it will undergo the reaction with CrO3, it will give you the ketone, right? Just now we did this type of thing, C double bond O, CH3. Okay, so this is my X, this is my Y, this is my Z. Okay, now you can see which among the following compounds have lowest and highest pK value. Okay, I'm having paranitrophenol, phenol, ethanol and orthocresol. Okay, so paranitrophenol is this. This is my normal phenol. this is my ethanol, CH3, CH2, OH, and orthocresol is this. In the ortho position, you are having one CH3 group. Okay, so here I am having one electron withdrawing group. Electron withdrawing group will always increase the acidity. So if it is having acidity high, right? So it is having acidity high means pK is lowest. pK is lowest here. Okay, now next if you just see this one, among these two, acidity will be low here because you are having one electron donating group. Here one electron donating group. So here acidity will be low. Acidity will be low. Okay, so if I just name it A, B, C, D. So acidity order, if I first decorate them, let me just arrange them. So acidity order, first will come A, after that it will come B, right? After that it will come C, after that it will come D. So pK order, if you see, just opposite. So pK value will be more in D, then C, then B, then A. Okay, just opposite, because lowest and highest pK value for this one, pK highest, and lowest pK value for A and highest pK value for D. Okay, I guess this is clear. Let's proceed. How is phenol prepared from benzene? Okay, benzene sulfonic acid, that we already did with the reaction. Sulfonic acid, oleum you have to treat, then NaOH and H+. How anisole react with methyl chloride, that also we did, Friedel-Crafts alkylation. And what is the effect of electron donating group on the alcohols? So acidity will decrease, right? That also something we did. So this is what that you have to cover in the alcohols, phenols and ethers chapter. First Williamson ether synthesis, Coles reaction, Riemann-Tiemann, Friedel-Crafts and esterification. Mechanism is dehydration of alcohols, dehydration alcohols to ether and alcohol to alkene, both. Okay, and hydrogenation of alkenes to alcohol. Okay, so these mechanisms are important. So if you can cover this thing and these questions, it will be more than enough to prepare the chapters. So yeah, let's proceed with the next chapter. Okay, so aldehyde, ketones and carboxylic acid. So this is the marks distribution. Very short answer type you can get 2 and long answer type you can get 2. Next, okay, question. This is the large answer type question. You can see, how would you prepare benzaldehydes from acetyl chloride and benzoyl chloride? So here you can see, you can proceed with the Rosenmund synthesis, right? Rosenmund synthesis, if you are having benzene with COCl, okay, then you have to treat this with H2 in presence of PDBSO4, right? You will end up with benzaldehyde. That is the reaction, right? How would you prepare aldehyde from the nitriles? That is a Stephens reaction. Okay, this is the reaction already done here. Okay, next you can see, how do you prepare the aldehydes from nitriles? This is the Stephens reaction. You have to treat this with SnCl2HCl. Okay, next name the reagent, oxidizing agent used in Etard's reaction, that is CrO2Cl2, that is called chromyl chloride. Okay, let's proceed. What is Etard's reaction? Explain. Already we did this in the previous slide. Next, how would you convert toluene into benzaldehyde? By using chromic oxide or chromic anhydride. So here you can see, first question we did already. Next question you can see, if you use chromic oxide for this case, wait. So chromic oxide will give you the benzaldehyde in this way. Chromic oxide in presence of acetic anhydride will give you this type of complex. After that, if you just hydrolyzed it, you will get the benzaldehyde. Okay, next, carbonyl group is more susceptible for the attack of the nucleophile. Justify your answer. So let me just show you. This is your carbonyl unit, right? So this oxygen group being electronegative, carbon becomes electropositive, so bond dipole moment direction is towards oxygen. So oxygen pulls the electron cloud density from the bond towards itself, making the carbon electropositive and susceptible for the nucleophilic attack. Okay, I guess it's clear to you. Let's proceed. Explain commercial method of manufacturing benzaldehyde by side chain chlorination. So this is a method. At first you just do the side chlorination in the side chain in toluene. It will give you benzyl chloride. Then you just hydrolyzed it. It will give you the benzaldehyde. Okay. Next, explain the Gattermann-Koch reaction. You can just simply start with the benzene ring. You can treat this with carbon monoxide, HCl and anhydrous AlCl3 in presence of CuCl. It will give you the benzaldehyde. Next, how would you prepare aldehydes from esters? Okay, so you can treat this, you can treat your ester with diisobutyl aldehyde, diisobutyl aluminium hydride, diisobutyl aluminium hydride to get the aldehyde from esters. Okay, let's proceed. This is the reaction you can see. Okay, aldehydes are generally more reactive than that of the ketone for nucleophilic reaction. So the reason is basically steric effect first. Because of the steric effect, you know, in ketone we are having the steric effect, 2 R group, but in aldehyde we are having only 1 R group. First reason, and another reason is electronic effect. So electronic effect coming from 2 alkyl group, making the carbonyl carbon comparatively more electronegative, right? So it making the ketone group less reactive than that of the aldehyde. Next, benzaldehyde is less reactive towards nucleophilic addition. Give reason. Because benzaldehyde is having 1 benzene ring, right? That makes the carbonyl carbon comparatively more electronegative. So why the nucleophile will attack over there, right? So that's why it is less reactive. Next, higher ketones like acetophenone do not react with NaHSO3. Give reason. So basically the steric effect, okay, the steric effect will not make the attack feasible over there. I guess it is clear. Yeah, let's proceed. Next question, what is the Clemenson reduction? You can see zinc amalgam HCl we can use over here. Okay, next, what is the Wolff-Kishner reduction? Give an example. Wolff-Kishner, same carbonyl will be reduced to hydrocarbon in presence of hydrogen in presence of ethylene glycol. Next, name the reagent used for the characterization of aldehyde and ketone, that is 2,4-DNP we can use. Proceed further, explain the test to distinguish between aldehydes and ketones. So we can use the tolerance test. Okay, aldehydes will give you the silver mirror precipitation out of it. Okay, aromatic aldehydes do not answer to Fehling solution. What is the reason behind it? Aromatic aldehydes, basically they are having 1 aromatic ring, right? So being 1 aromatic ring, the carbonyl carbon becomes very much electronically negative, right? So that's the reason Fehling's solution cannot oxidize that further. Okay, let's proceed. What is haloform reaction? Give an example. So haloform reaction, you can see aldehydes and ketone, at least 1 methyl keto unit should be there, COCH3 unit should be there. Then sodium halophalite, sodium hypohalite type of compound will give you the haloform or yellow precipitation of iodoform type of thing you will expect out of it. Okay, is isopropyl alcohol undergo haloform reaction? Okay, this is one example I gave here. You can see methyl keto unit is there. Okay, and here you will get the haloform, this thing. Okay, so next question was isopropyl alcohol undergo haloform reaction or not? Okay, so yes, definitely it will undergo haloform reaction. Why? Because of the secondary alcohol that under reaction condition it will first oxidize to ketone. Okay, so if it gets oxidized to ketone, then you can see 1 methyl ketone unit is present over here. So if methyl ketone unit is present over there, then definitely it will give you the haloform positive test. Okay, let's proceed. What is the aldol condensation reaction? So you can see aldehydes and ketones which are having at least 1 alpha hydrogen, it will undergo self condensation in presence of dilute alkali and it will form beta hydroxyaldehyde. On being further dehydration, it will give you alpha beta unsaturated carbonyl. Okay, so here comes the reaction. You can see this hydrogen and oxygen, you can just take it here and this carbon-carbon bond will be formed. Okay, and further dehydration can take place and alpha beta unsaturated carbonyl you can get out of it. That is aldol condensation. What is Candigiano reaction? Give an example. So here you can see aldehyde on being treated with concentrated alkali, it will give you the benzoate, right? It will give you the carboxylate ion and one alcohol. Okay, it's a kind of disproportionation type of reaction. Next, which type of aldehydes undergo Cannizzaro reaction? The aldehydes which are not having any kind of enolizable hydrogen, no alpha hydrogen should be there, they will undergo Cannizzaro. Why acetaldehyde does not undergo Cannizzaro reaction? Because it is having 3 alpha hydrogen, right? So I guess this is clear. Let's proceed. How would you prepare carboxylic acid from 1 degree alcohol? So simply you can treat this some oxidizing agent, right, KMNO4 or K2Cr2O7 to get the 1 degree alcohol. Next, how do you prepare carboxylic acid from the nitrites? So just simply hydration you can do. Nitriles being hydrolyzed, it will produce the amide. Amide again in presence of H plus and OH minus, it will give you the carboxylic acid. Next, how do you prepare carboxylic acid from Grignard reagent? You can just treat it with dry ice, that is CO2. Okay, it will end up with the carboxylic acid. Let's proceed. How do you convert acetic acid to acetamide? Just treat this thing with acetic acid. If you are having, treat this thing with ammonia, you will get acetamide. Next, how do you convert phthalic acid into phthalimide? You can see phthalic acid you can take, you can treat this with ammonia, then it will undergo release of water. Further, if you heat this, it will end with phthalimide. Then on strong heating, 1 unit of ammonia will be released and phthalimide will end up. Okay, proceed. What is this decarboxylation reaction? Give an example. Here you can see the process of removal of the CO2. Okay, that is called decarboxylation. Reagent is soda lime, you can use NaOH plus CaO. Okay, and decarboxylating reagent, that I already told you, soda lime. Next, what is Hell-Wohler-Zielinski reaction? Give an example. Hell-Wohler-Zielinski reaction is basically, I need to get one alpha halocarboxylic acid type of thing. You can see carboxylic acid containing alpha hydrogen reacts with chlorine or bromine in presence of red phosphorus. Okay, you will get alpha halocarboxylic acid, right? Next, explain nitration in benzoic acid. Explain nitration actually takes place, if I just want to write benzoic acid, if you are having, then if you just treat this with concentrated HNO3 and H2SO4, then you will get NO2 substituted in the meta position, right? Because COH group is meta directing. Okay, similarly for the bromination as well, your bromine will be attached in the meta position. Okay, that's it. So here you can see the concept that you have to proceed with. The name reactions are Rosenmund, Stephan, Etard, Clementian, Wolff-Kishner, Aldol, Cannizzaro, HVZ, decarboxylation, Fellings and Tollens. Okay, and mechanism you have to proceed with nucleophilic addition reaction, very important. Nucleophilic addition reaction in carbonyl. Okay, formation of acetal and hemiacetal. Okay, next aldol condensation, very important. Okay, I guess it's clear. Okay, so let's proceed with the amines part. So this is the marks distribution. You can see very small answer type you will get 2 and large answer type you will get 1. So okay, this is a question, 5 marker question. Which type of amines answer for carbylamine reaction? So definitely, as you know, the primary amine. Okay, reaction with an example. This is a carbylamine reaction. You can see RNH2 with CHCl3. This is the reagent in presence of KOH. It will give you isocyanide type of compound with a foul smell, right? Next, identify the compound X. So X is going to be benzene diazonium chloride, right? X is going to be N2 plus Cl minus. So now here if you give Ki, you will end up with this. Okay, I guess it is clear. Let's proceed. Okay, so for this case, explain carbylamine. Just now we did in the previous slide. Complete the following reaction. Okay, for this case, we will get, okay, just let me change the ink. Okay, in presence of NaNO2 and Cu. So first here you will get NO2. Okay, here you will get Na2 and here you will get NaBF4. Okay, Okay, next write the IUPAC name. So IUPAC name propanamine. Okay, let's proceed further. Explain the Hoffman bromamide degradation. Here you can see this is the Hoffman bromamide degradation primary amine by treating an amide with bromine in aqueous ethanolic solution, okay, of sodium hydroxide. So that is a degradation type of reaction. Okay, so next here you can see coupling reaction of benzene diazenyl chloride with aniline. It will give you a para amino azobenzene type of compound, that is a yellow colored dye. And here you can see the IUPAC nomenclature is also there in diethyl pentan 2 amine. Okay, let's proceed. How do you distinguish between primary, secondary, tertiary amine by using Hindenburg reagent with the chemical reaction evolved? So Hindenburg reagent itself is very much important for your upcoming examination. So this is basically benzene sulfonyl chloride. Okay, so if you use it with the primary amine, then it contains one acidic hydrogen, right? The product that you will get, it will be dissolved in base, right? But secondary amine, it will be insoluble in alkali, the product. Okay, but in tertiary case, in tertiary what happens, it will not react at all. Okay, that is the case. I guess it is clear to you. Next question, you can see give the preparation of para hydroxyazobenzene. Here you can see this is the benzene diazenyl chloride with the coupling reaction with phenol. It will give you the orange colored dye, okay, in basic medium. Okay, let's proceed. This is your Hoffman bromamide degradation reaction. Okay, already I explained, if you are having amide, then in presence of bromine and NaOH, you will get 1 degree amine, 1 carbon less system. Next question, pKb of aniline is more than that of the methanamine. Why? Because aniline is less basic. Why? Lone pair takes part in the resonance with the benzene ring, right? As a result of this, basicity decreases, hence pKb is more. So how would you prepare primary amine by Gabriel thalamide synthesis? It's here you can see this is a Gabriel thalamide synthesis. Okay, next, what are the advantages of Gabriel reaction? So here basically we will get purely 1 degree amine we will get. Okay, no 2 degree or 3 degree amine will be formed. Okay, next, aromatic primary amines cannot be prepared by Gabriel thalamide synthesis because where the steps are there na aryl halide, it will not undergo any kind of nucleophilic substitution with the anion that is formed by the thalamide. Okay, so aryl halide you can't take for the nucleophilic substitution. Okay, I guess clear. Let's proceed. Amines acts as a nucleophile or amines behaves as a Lewis base. Give reason because of the lone pair of nitrogen. Okay, lone pair donor. Next, aliphatic amines are stronger base than that of the ammonia. So this is basically the plus I effect of the alkyl group. Okay, next, aromatic amines are weaker base than that of the ammonia. This is because the lone pair of nitrogen, they takes part in resonance with the benzene ring. That's why the lone pair is not available for the donation. That's why it is a weak base. Next, arrange 1 degree, 2 degree and 3 degree amines in the increasing order of their basicity in gaseous medium. In the gaseous medium, 3 degree, then 2 degree, then 1 degree. Okay, and if it is in the aqueous media, then 2 degree come first, then 1 degree, then 3 degree, then ammonia. Okay, I guess it's clear. Let's proceed further. What is carbylamine reaction? So carbylamine reaction, you can see primary amine in presence of chloroform and KOH, it will give you the isocyanate, foul smell. Let's proceed. How does aliphatic primary amines react with nitrous acid? So it gives HNO2, right? Primary amine gives alcohol in presence of HNO2. Next question, name the gas liberated when aliphatic primary amine reacts with nitrous acid, that is nitrogen gas. Next, name the product formed when methylamine reacts with nitrous acid. Methylamine reacts with nitrous acid, it will give you the alcohol, that is methanol. Okay, What is diazotization? How does aromatic primary amine reacts with nitrous acid? That I already told you. Diazotization reaction, I guess also you remember. Aniline in the presence of HNO2, 0 to 5 degrees Celsius, it will give you benzene diazonium chloride. Okay. What temperature should be maintained for the diazotization? It is 0 to 5 degrees Celsius you can maintain. Next, what is coupling reaction? So these two coupling reaction, you can see this is benzene diazonium chloride with phenol, and with aniline. With phenol it will form orange colored dye, that is para hydroxyazobenzene, and with aniline it will form para amino benzene. Okay, para amino azobenzene, that is yellow dye. Let's proceed. Okay, so we will proceed with the next chapter, that is biomolecules. Here very short answer type we will get 2, short answer type we will get 1, and large answer type we will get 1. Okay, from here 2 marker questions are starting. So here you can see what are reducing sugar, give examples. So reducing sugars means that can reduce a Fellings and Tollens reagent. It is having one aldehydic unit, right? Like glucose, galactose, fructose, lactose, these are all reducing sugar, right? So let's proceed. What are non-reducing sugar? Give example. Carbohydrates that cannot reduce the Fellings or Tollens or Benedict solution. Okay, so they don't have the aldehydic unit, aldehydic or keto unit, okay, that cannot reduce. So okay, example is sucrose. Give 2 methods for the preparation of glucose. So first you can see from the sucrose we can do, if you do the hydrolysis, okay, if you do simple alcoholic medium, if you do hydrolysis, then you will get the glucose. Next, from the starch also, from the starch, by boiling starch with dilute H2SO4 you will get the glucose as well. Next, how glucose react with hydrogen iodide, or how do you show that glucose contains 6 carbon atoms in a straight chain? So basically if you treat glucose with HI in presence of red phosphorus, you will get a 6-membered chain. That will tell that yes, glucose containing 6 carbon system. Okay. Next, how does glucose react with hydroxylamine? So, as you can see, hydroxylamine reacts with the aldehydic unit and it forms glucose oxime. It tells us that yes, glucose contains 1 carbonyl group. Okay. Let's proceed. Next question, you can see how does glucose react with bromine water, or how do you show that glucose contains aldehydic group, right? So you just treat this with bromine water. So what happened? It will form the gluconic acid, right? So it will tell you that it has an aldehydic unit. How do you show the presence of alcoholic OH group in glucose? So basically, if you do the oxidation with the nitric acid, right, then both for the glucose or the gluconic acid, it will give you the dicarboxylic acid, that is called saccharic acid. Okay, so that will tell that yes, it is having the presence of alcoholic OH group. Okay, next, write the open chain structure of the Emil Fischer structure of glucose. This is the open chain structure of glucose. Okay, let's proceed. Give the limitation of open chain structure of glucose. So here you can take the example like it contain the aldehydic group, but it do not respond to the Skipp's test, right? And also it don't give the addition product for when it is reactive with the when it reacts with the NaHSO3. Okay, next, one more you can give. D-glucose is found to exist in 2 different forms, alpha and beta. So this type of example you can give. Next, what are epimers, what are anomers? So epimers are when they differ in their configuration at any 1 carbon, that is epimer, and anomer is when sugar with different in their configuration at C1, okay, only in C1, that is the first carbon, that is anomer. Next, this is the structure of glucose and glucopyranose. Here you can see this 2 you can represent like that. Next, write the Haworth structure of alpha D maltose. Okay, so here this is how you have to draw the structure. Alpha D glucose and alpha D glucose, you have to just merge them with the glycosidic unit. Okay, next, mention the type of glycosidic linkage in maltose. So glycosidic linkage is basically carbon 1 of glucose is attached with carbon 4 of another glucose. That is basically the glycosidic linkage. Okay, next, give reason maltose is a reducing disaccharide. So basically it has a free aldehydic group, okay, that can be produced at C1, carbon 1. Okay, so that's the reason it works as a reducing disaccharide. Let's proceed. Write the Howard structure of lactose. So this is the Howard structure of lactose. You can see. Mention the type of glycosidic linkage in lactose. So basically carbon 1 of beta D galactose and carbon 4 of beta D glucose, they are linked. Okay, give reason why lactose is a reducing sugar. So again, free aldehyde group is present at carbon 1. Okay, that's why it is a reducing one. Name the storage polysaccharide present in animal where it is found, that is the glycogen, it is found in liver, muscle or brain. Give any two difference between starch and cellulose. Here you can see alpha D glucose it is made up of, and cellulose it is beta D glucose. You can talk about the bond, you can talk about the branched and linear structure, like that. Okay, let's proceed. What are essential of alpha amino acids? Give example. Essential alpha amino acid, they cannot be synthesized in your body, you have to consume it through diet. Okay, lysine, valine, etc. Next, non-essential means they can be synthesized in your body, like alanine, glycine, etc. Let's proceed. Zwitter ions or dipolar ions. Zwitter ions basically COOH is a H donor, hydrogen proton donor, and NH2 group is proton acceptor. Both of them present in the amino acid, right? So whenever it forms CO minus by donating one H plus, and NH2 accepts the proton and it forms NH3 plus. So dipolar version of the amino acid we get, that is called Zwitter ion. Next, how are proteins classified based on their molecular formula? So they can be classified into fibrous and globular. Fibrous you can explain in accordance to their structure, solubility, presence. Okay, some example you can give: keratin, myosin, collagen. Globular protein you can explain the shape of it, you can explain some example, like that. That will be more than enough. Next, denaturation of protein means whenever the chemical or because of some chemical changes like pH, temperature, okay, physical change also can be done, the protein breaks down. Okay, the alpha the hydrogen bond of the protein, they gets disturbed. Okay, because of this disturbance, what happens, the protein get denatured. Okay, the physical activity or physical activity of protein or biological activity of the protein, they get disturbed. That is called denaturation of protein. Okay, next, which level of structure remaining intact during the denaturation? That is a 1 degree. Next, explain the classification of vitamins. So water soluble and fat soluble, you can write fat soluble A, D, E, K, and water soluble B and C. Okay, next, these are the vitamins. Important thing is which vitamins, where we can find it, and in case of deficiency, what type of thing we can expect. Okay, vitamin A from where, like fish liver oil, carrots. In vitamin A absence, we can face xerophthalmia, night blindness. Vitamin B, that is thiamine, we can get it out of milk, green vegetables. We can face berry, right? Next, vitamin B12, that is called riboflavin. Okay, that we can get out of egg white, liver. We can expect some fissuring of corners of mouth and leaf. Okay, so this type of thing. Next, you can see vitamin B6, B12, vitamin C, D. In accordance to that, different type of disease you have to remember. Anyone can be asked. Okay, give the difference between DNA and RNA. So here comes the difference, you can see. Next, hormones. A little bit about hormones means which type of hormone, how they are working, and let's say I'm having give one example of a amino acid derivative type of hormone or steroidal hormone. So that type you have to remember, like steroidal hormone like estrogen, androgens, amino acid derivatives like epinephrine, thyroxine, norepinephrine. These type of things you have to remember. Next, here with respect to functions, they can ask you the hormone that is responsible for the blood glucose regulation, that is insulin and glucagon, you can talk about. They can ask you about the thyroxine gland. Okay, so you have to mention about both hypothyroidism and hyperthyroidism. Okay, so like that type of question you can expect out of hormones. Any one hormone can be asked out of it. Okay, now steroidal hormone, they can ask you to write down any one steroidal hormone and along with their function. Okay, and also they can ask this type of question, any one disease they will take, like Addison's disease, because of which hormone you will get this, we will face this type of disease. Okay, so that time you have to tell that malfunctioning of the any one of the adrenaline cortex hormone. Okay, adrenaline cortex itself, if it malfunctions, then you can get like glucocorticoid, mineralocorticoid, all will be not functional properly, right? Here comes some more hormones you can see, and you can just you just have to remember the functions like testosterone, estradiol, progesterone, etc. If we proceed further, write the Howard's projection of sucrose. So this is how you have to represent that. Give reason sucrose is a non-reducing sugar. So I already told you, if that particular group, reducing group is not present, right, in sucrose, like yeah, glucose and fructose are there, but those aldehydic unit of glucose and fructose, they involve in formation of the glycosidic linkage, right? So that's the reason they are not free to reduce the Benedict or Tollens or Fehling solution, right? Next question, mention the glycosidic linkage in sucrose and cane sugar. So basically alpha D glucose and beta D fructose. Okay. Next, what is invert sugar? It's a very important question. Invert sugar is basically sucrose is dextrorotatory, but after hydrolysis it gives dextrorotatory glucose and levorotatory fructose. Levorotation of fructose is more than that of the dextrorotation of glucose. So that's why the mixture appears to be dextrorotatory, right? So the hydrolysis product becomes opposite side, right? So as a result of this, we call it invert sugar. Okay, next, this is the glycosidic bond, two monosaccharide joined together by an oxide linkage. How it is formed? By loss of 1 unit of water. Okay, let's proceed. Okay, name the storage polysaccharide present in plant. Name the monomer unit present in starch. Name the components of starch, and write two difference between amylose and amylopectin. So storage polysaccharide, that is starch, monomer present, amylose, amylopectin. Okay, so next, component amylose and amylopectin you can proceed with. Okay, monomer is basically glucose, you can write. Okay, glucose is the monomer of starch. Next, two difference, here comes so many difference, you can pick any two and you can just mention. Here comes, you can see different types of disaccharides and polysaccharides and their monomer units and their linkage. Okay, you can just go through them. It will be helpful sometimes, like for the starch, lactose, maltose, sucrose. Okay, this is important. Next, that's it actually. So what you have to remember, basically carbohydrates, in carbohydrates different reaction with the glucose. Okay, disaccharide and polysaccharide, reducing, non-reducing sugar, that's it. Proteins, you have to remember the structure of proteins, how the peptide bond is formed, what is zeta ion, essential, non-essential amino acid, that's it. Vitamin, you have to proceed with the fat and water soluble different type of vitamin. Okay, one more thing, in protein you have to also go through the structure. Okay, Acha, vitamins, you have to proceed with the different deficiencies of vitamins and that causes the disease. Hormones, you have to proceed. In hormone, you have to proceed with the functions. Then nucleic acid, you have to proceed RNA, DNA. The difference will be more than enough, and the structure. Okay, so I guess yeah, that's enough. That's enough for the complete organic portion. If you can complete this many questions, I guess it's not I guess, it's quite sure that you will get 65 plus, and don't worry about it. Whatever the question will come from the organic chemistry, if you have covered this much, you can attempt all the question out of it. Okay, that's my assurance for you. So yes, for this many effort, I'm asking you just to give one thumbs up to this particular video. Don't forget to share with your friends as well, and if you have not subscribed this channel, please do subscribe. And finally, thank you for watching. All the very best for your upcoming examination. Thank you.